So can you see my screen here?
Yes, sir. I got it.
All right, perfect. So frequently recently, this presentation was actually developed for water treatment training by the Northwest subsection of PNWS, which then was canceled. And then it was also submitted to PNWS, the regional conference, which then was canceled. So it's good to finally be able to give this presentation. And it's just meant to be a general overview of disinfection and water treatment. So moving along here, here's just a kind of an agenda slide of the things we're going to cover. Start on a little bit of the history of disinfection, different types of disinfection, similar to the poll question we had earlier. A little into chlorine dosing theory, and then we'll really hone in on chlorine systems and the various components. And hopefully set the stage well for other presentations that follow here. So a look back at the history and why we disinfect water. I think really, even still today, waterborne illnesses are a very large factor in human mortality. I think the most recent statistics I saw is that about 3.4 million people die every year from waterborne illnesses, and that's today. Of course, that's more focused in developing nations that have issues with access to clean drinking water, not so much in developed nations where we've implemented very robust water treatment. What really kind of started the look at disinfection was in the 1800s. There was multiple pandemics of cholera that went all around the globe, and people started really looking into, well, what's going on? And the original opinion was that the cholera was being spread through interpersonal interactions, but an English physician named John Snow actually went and he started researching a cholera outbreak in England, and what he found was that it was linked to a drinking water well, and that drinking water well was pulling groundwater under the influence of surface water that was just downstream of where they were dumping untreated sewer into the Thames River. And he really became the father of epidemiology in this work, and which is of course something we hear a lot about now. And one of the things that he looked into was actually treating the water using chlorine. However, early on, he ultimately just ended up taking the pump off, the handle off the pump so folks couldn't use it, and the local outbreak of cholera subsided. But this really got people interested in water disinfection, and by the 1890s there was a lot of research done and published on the use of chlorine for water disinfection. And the first city to actually implement water disinfection was Maidstone, England, and they completely chlorinated their water supply with gas chlorine just before 1900. About 10 years later, it followed and made its way to the United States, where a city in New Jersey implemented chlorination using calcium hypochlorite. And from there on, chlorine kind of expanded across the developing nations, and just about everybody started using it. And from the smallest city to the largest city, and here on the right, you can actually see it's a picture of a soldier during World War II drinking out of what's called a Leicester bag, which is just a canvas bag with a couple calcium hypochlorite pucks in there for water disinfection. And that was used by the military from World War I all the way through the Vietnam War. So it really became a background, the backbone of clean water. So what are we trying to accomplish with disinfection? There's a couple things. We're taking water that potentially has microorganisms in it or viruses that exist right now and have potential that impact human health. So we want to kill those right away. But the other part of it is then we're taking this water, we're sending it down a pipeline, and it's going to be around for a little while before it gets consumed by people. And, you know, those distribution systems aren't necessarily absolutely perfect. There may be some leaky pipes or ways that other things can get in. So we want to maintain a residual of that disinfectant to prevent future growth. And as I noted here, this is absolutely required. It has to happen. So there's a few different types of disinfection, and some offer different benefits. So it's really breaks down into two different groups, which are chlorine-based disinfection. So chlorine compounds, chloramines, chlorine dioxide, or other types of disinfectants such as UV and ozone. UV and ozone offer you that initial kill of microorganisms, but they don't help you maintain a residual. And as noted here, chlorine and chloramines are your only options for maintaining a disinfection residual. So what's the difference between these two? Chlorine compounds are sodium hypochlorite, calcium hypochlorite. They're just a source of chlorine that can be put into the water. They're very commonly used. We saw in the poll, I think about 70% of people were using chlorine at their plants. They're very economical. It's not a very complex chemical. It's fairly easy to produce and transport. The drawback to chlorine is that in certain water qualities, it can form what are called disinfection byproducts, and certain high levels of disinfection byproducts can be harmful to human health. So you have to know your water quality before you decide that you're going to proceed with chlorine. Chloramines are they're chlorine ammonia compound, and they're nice because they offer a longer lasting residual in the disinfection system. And again, they have a lower risk of DPP formation. That said, they are a little more expensive to deal with and that type of thing. And so generally, unless you have that driver for DPPs, people will look at chlorine over chloramines. So moving along, looking into dosing theory, this is a graph that reflects what's called breakpoint chlorination. And effectively on the bottom, you have the amount of chlorine you're adding. And on the left, you have the amount of chlorine that you're reading in your residual. And effectively what happens is when you're metering in chlorine, initially you're not going to contribute to any type of residual. Then you're going to hit a point where you start forming actually chloramines, and your chlorine residual will creep up. And then as you add additional chlorine, it actually goes down, and then it encounters what's called a break point. And when you hit that break point, at that point, all the chlorine that you add after that point will contribute to a residual that you'll maintain in that water until some point that it is consumed. So for residual chlorine management, you need to be dosing past the break point for your water. So we've talked about chlorine and chloramines, and we'll kind of hone in now on chlorine systems. And that's because, as we saw here today in the poll, that's very common in the Pacific Northwest, just because we have pretty good raw water that doesn't have a ton of disinfection byproduct forming potential. Obviously, that's not a hard and fast rule, but that's kind of a generalization. So here's a very schematic figure of a standard chlorine system. Really, there's four components that you have, which are first a chlorine source. Where are you getting that chemical from? Next, you need to have dosing pumps, which is just the ability to meter that into your water. You need to have analyzers so you know how much you're adding in and how much is being maintained in the water over time. And you also need to have a contact basin or a pipe or something upstream of your first customer to allow that disinfectant time to interact with your water and make sure that it's dispersed evenly and it's taking care of anything that's in the water. You know, I noted here that there's a lot of other components that go into this. There's different other constituents in the water you need to analyze as part of chlorination, but these are really the main components of chlorine system and what we're going to go through here. So first, chlorine sources. There's 5 chlorine sources. First being gas chlorine. Also, there's bulk sodium hypochlorite. There you can do on-site generation of hypochlorite. You can also do on-site generation of high-strength hypochlorite, and you can also use calcium hypochlorite. And we'll go through each of these here. Gas chlorine. This was the one that the first chlorination system ever when Maidstone, England used gas chlorine. And historically, it's been a very low-cost alternative for chlorination. It's a very, very simple system. It basically consists of taking a container that has chlorine gas in it and allowing that gas to go into the water. However, chlorine gas is also a very, very toxic gas. It's been used in war. So there's definitely there's health and safety concerns on how you handle it and how you mitigate the potential for those cylinders to leak within your plant and expose your operation staff or potentially your neighbors to chlorine gas. So there's very, very strict health and regulatory requirements for leak monitoring, leak prevention and containment. You need to have risk management plans in place, and you need to have a very robust staff training to make sure that your people that are working on these systems are doing it in a safe manner and are taking care of themselves. But in the lower right here, you can see a schematic of what a gas chlorine system looks like, and it's very, very simple. There's not a lot to it. You really just have the gas itself, and it goes over to the water. Next is bulk sodium hypochlorite. Sodium hypochlorite is just basically household bleach, but bulk is available at higher strengths than you can typically find in your local grocery store. Typically, it's around 12.5% strength. And what's nice about this is you just need some tanks. You have a tanker truck come to the site, they fill you up, you store that chemical, and you dose out of those tanks. And as soon as you need more hypochlorite, you just contact someone and have them bring you more. Some of the drawbacks with this is that the solution itself will degrade over time and you'll lose strength. The other challenge with this is that when sodium hypochlorite does degrade, it off-gasses. And that off-gas basically just puts gas into your chemical dosing system, and you need to design it in a way such that that gas buildup doesn't damage or also just clog up and harm the operation of your system. But again, here in the lower right, you can see really you have some tanks, storage tanks that you have a fill station for. It's best practice to have a day tank, so you need a small transfer pump to move it over to the day tank that you actually do your dosing out of. So again, a very, very simple system overall. Moving up a little bit in complexity for these systems is low strength on-site hypochlorite generation. Basically what this does is if you apply a DC current to a saltwater solution, a brine solution, it will create a very low concentration of hypochlorite. What's nice about this is all you need to do is bring in salt, water, and power to produce that hypochlorite. And the other thing that's nice about it is that at that concentration, it's not a hazardous chemical to handle. One of the things to note is that these units do produce hydrogen gas as part of their operation, and you need to have a way to vent that outside. And you can see in the schematic that there is a lot more components to a low strength hypochlorite generation system. However, what's nice about it is your operations staff really only need to handle salt, which obviously is not a hazardous thing to have to manage. High strength on-site hypochlorite generation is basically the next level up from low strength. And basically it entail having the same equipment that your bulk hypochlorite supplier uses to make the chemical before they bring it to you, but now you own it and it's on your site. It's a little more complex because it's really the same operation as the low strength, but there's also caustic soda that's used in the process, which is just another layer of things you have to work on. But, and again, a byproduct is hydrogen gas, and you need to make sure that you ventilate that outdoors. And lastly here, the first chlorination system used in the United States, calcium hypochlorite. Really, calcium hypochlorite dosings are chlorine systems are not that different from the Leicester bag shown earlier. You have a tank. Inside that tank, you put calcium hypochlorite pucks. You bring water into that tank. The water dissolves calcium hypochlorite to its saturation point, and then you dose out of that tank itself. So it's a very, very simple system. It's basically a tank. You don't deal with having, large tanks to store the chemicals and that type of thing. One thing that's important is you need to make sure those calcium hypochlorite pucks are stored in a cool, dry, dark area, because they are a very corrosive chemical. So what does this all mean? So what I've included here is just kind of some trends of what can be seen around in the area for who's using what. Gas chlorine is no longer a widely used alternative just due to the health and safety concerns. There are some plants that still use gas chlorine and do so in a safe manner. However, you don't see a lot of new applications. Bulk sodium hypochlorite, very simple, not a lot to deal with. It's very commonly used, and it's especially commonly used in very large plants where you're dealing with multiple tanker trucks loads of demand, and it kind of makes it a little more economical. Low strength on-site hypochlorite generation is a more complex system, but it's growing in popularity of its use, from the smallest well site to even larger treatment plants. One of the things that's really nice in the smaller remote kind of well sites is that your operation staff only need to be hauling salt around out to these facilities as opposed to hauling out liquid chlorine of some type or gas chlorine cylinders. High strength on-site hypochlorite generation is very, very complex, and as such, it's not really used. I'm not aware of anywhere in the Pacific Northwest that is using that. I believe there's some large plants on the East Coast that do use it, or at least have really considered going to this. And last but not least, calcium hypochlorite saturation. Again, a very simple system, and very, very commonly used, and particularly in smaller systems. When you're looking at deciding if you need to implement chlorination or you are looking at going a different direction, there's a couple ways to look at. One would be a life cycle analysis, where you look at, not only what does this cost now to implement, but what is it going to cost me over 20 years? Or you can also do some type of weighted analysis where you prioritize what's important for you and your system. For example, if one of these systems has a lower 20-year life cycle cost, but you only have 2 operators, and that particular system is really, really operator intensive, then you probably wouldn't want to go with that. So in that situation, it would make sense to add more importance on operator effort in your analysis. So moving down the line here, once we have our chlorine source, we have to have a way to actually introduce it to our water, and that's where chemical dosing pumps come in. There's a lot of different types of dosing pumps, but the ones that we primarily see in drinking water are diaphragm pumps and peristaltic pumps. Diaphragm pumps are a type of positive displacement pump. They work using a diaphragm and piston and inline check valves. Basically, you can see in the diagram below, The piston retracts, the diaphragm pulls back, that creates native pressure inside the cavity of the pump, allows the inline check valve on the upstream side to open up and allow liquid in, and then the diaphragm compresses, displaces that liquid, forces the downstream check valve to open, and pushes that liquid out. And that displacement is a very well-known volume, so it's a highly accurate way to dose chemicals. These pumps come in a wide range of flow rates and accommodate feed pressures up to about 250 psi. Peristaltic pumps are another type of positive displacement pump, but they operate with a roller, rotor and rollers, and then tubing. And basically the tubing wraps around the rotor, and when the rotor turns, it compresses that tubing and contains a small known amount of chemical and pushes it around the tubing. Again, that's a highly accurate way of controlling chemical dosing. And these come in a wide range of flow rates, and they offer feed pressures up to 125 psi. One of the things that you have with peristaltic pumps over diaphragm pumps is you can imagine as you're constantly all day long squeezing this tube, eventually it's going to get brittle and wear out on you. So you have to not only select the right type of tubing for the chemical and the feed pressures you're dealing with, but you're also going to have to replace them over time. A quick word on sizing pumps. You know, a bigger pump isn't always the best pump. The way these positive displacement pumps work is that they operate and stroke and push small slugs of chemical out. So if you offer a very large pump for a very small demand, that pump is only going to operate very infrequently. And that's going to really create ups and downs in your process control, because you're going to be basically slug dosing small amounts of chemical very infrequently into your water. On the flip side of that, if you have a pump that's too small for your demand, it's going to be working too much. And if it's a peristaltic pump, you're going to be wearing out your tubing way too fast. If it's either a diaphragm or a peristaltic pump, you can wear out your motor. So it's best to make sure that your pumps, which cover a large range, that capacity that you're really trying to hit is right in the middle of their range. And then in terms of which pump is best, I've found that everybody has their own opinions on that. So I think it's just best to spend some time with both and figure out what works best for you. So, moving along again, chlorine analyzers. This is another part that you need to know how much chlorine you're putting into your water and what your residual is. There's two types of chlorine analyzers: colorimetric analyzers and amperometric analyzers. And there's kind of two different types of samples that are done too. There's a grab sample where you actually go out with a container and you take a sample of the water. And then there's also continuous online sampling. We'll focus a little more on the online samplers. Colorimetric analyzers operate by taking chlorinated water and mixing it with a reagent. And a reaction occurs with that reagent, and depending on the amount of chlorine you have in your water, it creates a colored solution. And then the colorimetric analyzer can actually detect the chlorine dose just based on how much color there is in the water. What you have with these, though, is you're constantly consuming reagent, and you're going to have to replace those. Next, yes. Holy cow. All right. I had a lot more to cover, but I think we're going to have to kind of breeze through some of it here. Amperometric analyzers, they're a reagently process where they actually measure the current between two analyzer probes. These require periodic recalibration, but very infrequent probe replacement. So overall, you don't have as much O&M with these systems. They are a higher initial cost. We'll move through quickly. Next in the system, you have contact basins. These are basins or pipelines that are dedicated for giving your chlorine time to react with your waters. This contact is referred to as CT, which is a representation of your chlorine concentration multiplied by your contact time in minutes. Your CT requirements depend on a lot of things, primarily whether you're treating surface or groundwaters, but also your pH and temperature. So how do you get this? And again, you get contact time by providing a pipeline or tankage. Here on the right is City of Anacortes, their Clearwell, which is a 2.1 million gallon tank that's specifically designed to have chlorine interact with your water. The time you use for a CT calculation is based on the hydraulic detention time of the basin, but that has to account for any hydraulic inefficiencies within that basin. So what that looks like, you can see in the figures here on the right. Basically, if you don't have anything within a contact basin to force the water to move evenly throughout the basin, there's going to be flow paths that develop and the potential for certain water to move through that basin faster than others. And the challenge with that from a human health perspective is that hasn't had its contact time yet necessarily. So what you have to do is basically derate the time that you can claim as part of the CT calculation based on the efficiency of your clear well. So here's an example design of a project that I'm working on now, actually for City of Anacortes. We're installing a second clear well for them. And what we've done is on the upper left, you can see the figure. This is a plan view of the clear well itself. And the red lines are interior baffles that are made out of like a ship sail material that's designed to be in contact with the water. This forces the water to move through the basin in a serpentine fashion and prevents a lot of that short circuiting. Also on the right, you can see that our inlets and outlets are baffled so that the water is basically diffused out of them as opposed to creating some sort of velocity gradient or something in the water. For this system, we're only claiming 0.3 baffling factor, which when you look at the baffling descriptions, that would be what you would assume for an unbaffled inlet and outlet with no basin baffles. And the reason that we're only assuming a 0.3 is because what we've seen, and the Washington State Department of Health did a big tracer study a few years ago of 32 different plants across the state and found that theoretical baffle factors, if you apply the guidelines from the surface water treatment rule, seem to poorly correlate with the actual performance. They seem to be actually a little optimistic. So tracer studies, basically you dose a chemical into a contact basin and you measure the time it takes for 10% of that tracer chemical to be detected. And you compare that to the theoretical detention time. And that will show you what the efficiency of your contact basin is. And their tracer studies are required on any new contact basin that's constructed. And that's just to make sure that your theoretical assumption during design is in line with what you need or in line with reality. So the best thing to do, therefore, when you're planning to build a contact basin is to be conservative with your assumptions, just to make sure that you have what you need. So quickly here, wrapping up, again, you know, your chlorine source, your chlorination system consists of a chlorine source, dosing pumps, analyzers, and contact basins. And when you're making decisions on what direction to go with any of these, it's important to identify and prioritize what's important to you, your plant, your staff, and the people who you're providing water to. And a great way to do that, and it can be such a challenge now that we're not interacting as much as we used to at conferences and that type of thing, is to communicate with those around you. And that knowledge share between plants and between different operators and between different engineers is so incredibly vital in how we move ahead and make sure that we are doing the best we can to provide clean drinking water. So, and the last thing here is just it goes for contact basin design with baffling factors, or making sure you have a resilient system with an earthquake, but is to hope for the best, but plan for the worst, and make sure you have things in place. So with that, I'd like to say thank you, and also open it up for questions. I doubt that. It's early. Early on Thursday.
Yeah, can you see my screen all right?
Hello. Hi. No. Hey everyone, thanks for showing up today. And I'm Juanita, as Josh mentioned, and Amanda and I are here to present when the hypochlorite stars don't align, choosing between bulk or on-site for PWB's Washington Park. We wanted to summarize in this presentation the decision process that we went through with the help of Kennedy Jenks in the early design phase for the hypochlorite project at Washington Park. We were deciding between bulk hypo or on-site generation for a chloramine boosting system. So as Josh mentioned, I'm Juanita Hess, and this is Amanda Masick, and we hired Kennedy Jenks as our design consultant for this project. And Washington Park. So some of you may know, it's a very historic Portland favorite. It was also part of the original water system designed in, let's see, that's a slide in the future. Getting ahead of myself. It's located in the West Hills. Next slide, Amanda. Over on the left, you'll see the greenery there, and not sure if you can make out the text there, but if you can see, there's kind of a rendering laid into the hills there. That's the project, just adjacent to downtown. Burnside Street is the one with the bridge that's horizontal, and you'll see the stadium there if you're a Timbers or a Thorns fan. And over closer to the bottom right along the river, there's the federal building, which is maybe more relevant in these days. So next slide. Washington Park was built in 1894 as I mentioned, part of the original water system designed by our ever so thoughtful forebears. It was constructed as these reservoirs, Reservoir 3 and 4, were constructed as open water reservoirs, gravity fed to the downtown and further reaching western portion of Portland. And these reservoirs remained online for well over 100 years before they were decommissioned for basically OHA and federal water drinking regulations required us to take our open reservoirs offline. And so that's when we started the current Washington Park Reservoirs Improvement Project. So the park itself, reservoirs and structures included, is a very endearing place. As you can see, it's beautiful views, historic structures, neighbors, visitors. The city itself loves the character and the views in the area, and it's on the list of historic places. So there were some limitations in developing even our hypochlorite project, but for the larger projects, huge involvement with neighbors and the historic preservation reviews. And another interesting part of this project was that it came in after the Washington Park Reservoirs Improvement Project started, so we're also coordinating with that project. Here's the site we're looking at. The upper portion here, there's can you show them where the building is, Amanda? On the right upper, that's the chlorine building, and the reservoir project is underway, and we're just working with them. Reservoir 4 is the one on the right adjacent to the building. That one is going to be, that one used to be a open water reservoir. Now it's going to be more of like a drainage pond with a reflecting pool feature. The greenish part underneath is like a stormwater swale type area. And the reservoir on the left is Reservoir 3. They're constructing a an underground, about 13 million gallon reservoir, and then the water feature on top. We had to include water features for this project because the neighborhood and historic preservation required it. So it's going to be really beautiful. Where are we at? So we're in the middle of construction for the Washington Park Reservoir. And as I mentioned, the underground reservoir is about 13 million gallons, seismically reinforced. And as I mentioned also, it's got the reflecting pool on top. And I think Amanda's gonna take over from here.
Yeah, thanks, Juanita. So as Juanita mentioned, because we added these reflecting pools as part of this project, there's a new need to provide chlorination to the pools to maintain their water quality, which kind of brings us to this project. So as Juanita pointed out, the hypochlorite building where this improvement project is located is situated adjacent to the lower reservoir. The hypochlorite facility was originally constructed in 1981 as a chlorine gas facility. It was decommissioned in 1993 and upgraded to bulk sodium hypo for safety reasons. Because the facility was originally intended to be a gas facility, it's rather small. It's a total of 920 square feet, with the main room being what was the chlorine storage room. There's a smaller room to the right, which was the chlorine feed room, and then a controls room located in the back. And the sodium hypo system is in really poor condition, and it's no longer operational. So Portland Water Bureau isn't currently doing any chlorine boosting to the distribution system at this facility. And so with the reservoir improvement project underway, the Water Bureau had the need for a functioning chlorine facility to maintain water quality in their reflecting pools. And so they developed an internal project validation report to determine which alternative they should move forward with. And the report evaluated 3 different alternatives. The first one being to only disinfect the new reflecting pools and provide chlorine at the facility. The second being to disinfect the new reflecting pools, but also provide the ability to boost chlorine in the distribution system again. And then the third option being to disinfect the new reflecting pools, but to boost chloramines in the distribution system. In Portland Water Bureau's water quality group wanted the ability to boost chloramines in the distribution system. And since they're already treating with chloramines, so there wasn't an interest in providing chlorine boosting. And so the recommendation from the report was to move forward with alternative 3, so to disinfect the reflecting pools and to implement the chloramine boosting. And the report went even further to provide potential dosings for the pools in the distribution system. And with that, they concluded that on-site generation wasn't a feasible option due to the cost, and that bulk sodium hypo is the preferred methodology for the project. However, when we showed up to the kickoff meeting for the design, ops came in prepared with their case for changing the design to on-site generation. And it spurred revisiting the initial conclusion of the PVR that bulk hypo is the preferred source of sodium hypochlorite. And their main reason was that the usage rates were inflated, making bulk hypo look to be more feasible when really the comparison should have been more between a mini bulk and on-site generation. And so this had us take a step back and take another look at on-site generation and bulk sodium hypo to determine if bulk hypo really was the best option for Washington Park. And so from there, we went ahead and evaluated on-site versus bulk sodium hypo while keeping the project goals in mind, which were providing 3 chloramine boosting locations for Portland's West Hills and providing chlorine treatment to the 2 new reflecting pools. And Kenneth did a great job earlier describing the difference between chlorine and chloramine in the last presentation, with the main difference being that chloramine includes the addition of chlorine, and in this case, sodium hypo, and ammonia, which produces a more persistent disinfectant than using free chlorine. And chloramines are what Portland Water Bureau uses for disinfection. And because they're already using chloramines, if they were to just add chlorine for boosting the residual, it would have a negative effect of altering where they're operating on the breakpoint curve. So that's the reason for the water quality group to want the ability to boost chloramines versus the free chlorine in their system. And then because the decision was to boost chloramines in the distribution system, concern needs to be taken for how to properly handle sodium hypo for water quality concerns. So one of the main drivers in choosing which path to go down between bulk or on-site hypo is the effect of disinfection byproduct formation on water quality. Because the sodium hypo degrades, perchlorate and chlorate are formed. And perchlorate and chlorate are both currently unregulated disinfectant byproducts from the EPA. They're both linked to health concerns, and in particular, they're linked to the inhibition of thyroid iodine uptake, which has a negative effect on mental and physical development in young children, especially. And chlorate is currently monitored by the EPA as part of the 3rd unregulated contaminant monitoring rule, where 30 different unregulated contaminants in public water systems are tracked. And there's currently no federal regulation, but the EPA has established a recommended limit of 210 parts per billion. And perchlorate, on the other hand, isn't regulated at all by the EPA, but multiple states have incorporated limits into their drinking water standards, with Oregon having a max residual disinfectant level of 4,000 ppb per chloramines. And for instance, California has a limit of 6 ppb for perchlorate in their drinking water. And so because of the danger of introducing disinfection byproducts into drinking water systems, AWWA has released some best practices for how to handle sodium hypo to limit their formation. And the first one is to conduct operations so that you're minimizing storage time and using fresh hypo as much as you can, which is ideally within 30 days, but up to 90 days. For example, you don't want to add new chemical to the heel of an old tank either. So you want to use slope bottom or conical tanks to ensure that your tanks are empty before you're adding new chemical to them, and to make sure that you're using your freshest chemical as fast as you can. The second best practice is to use high quality filtered sodium hypo. And a higher ion strength favors higher reaction rates, such that you're forming disinfection byproducts at a more rapid rate when you're using unfiltered hypo. And then the third best practice is to dilute your hypo solution immediately after delivery, because diluting hypo by a factor of 2 decreases chlorate formation by a factor of 7, which is pretty significant, especially if you're not planning on using it very quickly. But obviously this requires much more storage volume. And lastly, you want to store hypo at low temperatures. The recommended temperature to store it at is 60 degrees Fahrenheit, but every 3 degrees you are above the recommended 60 degrees Fahrenheit, you're doubling the formation of disinfection byproducts. And so with these best practices in mind, we took another look at on-site sodium hypo, which would produce a 0.8% hypo solution, which is below the hazardous material threshold. And OPS was really into the idea of not having to handle a high strength hypo solution at the facility. On-site also has the benefit of being able to alter your production rates to meet your demands. And in this case, where we didn't really have a good grasp on what their anticipated demands were, it would allow the system to be adaptable so that you're not having to get a lot of extra chemical when you may or may not necessarily need it. But the downside of this is that it has a higher capital cost, and you really need to be able to receive bulk salt deliveries to be cost effective. You could potentially go down the path of dealing with bags of salt, but that not only requires more cost for the salt itself, but more cost in time from your operations staff to be managing the facility. And with this facility being like up in the park and not necessarily one of Portland Water Bureau's main facilities, it's not going to be staffed full time, and ideally it would be a little bit more hands off for operations than that. And with the bulk delivery option, the storage tank to accommodate this is huge. So there wasn't a way to fit it within the existing building. It would have had to be an exterior tank. And so looking at bulk sodium hypochlorite, it has the benefit of already conforming to the treatment that Portland Water Bureau uses at their groundwater facility, which is Portland's secondary drinking water source, with Bull Run being the primary source. And the project has the added benefit of having a scope and budget that has already been approved by the Water Bureau. But then it had the downside of operations not being supportive of the decision, and it's really hard to manage in a small building footprint. If you look at the picture on the left, that's actually the existing bulk hypo facility that they ended up decommissioning. And part of the problem was that just to fit the tanks and pipes and skids and everything else into the building, it was really tight space and hard to maintain. It was hard to access and repair any leaks, and just wasn't a feasible setup for having bulk sodium hypo in such a small room. So looking at the overall constraints, the major ones were that it's hard to change the existing scope and budget that was already approved. The existing building footprint being really small that it's hard to fit, honestly, either of the options into them while still getting everything that you would ideally want. And then lastly, being located in Washington Park, there were multiple codes to navigate and deciding what improvements could be made to the facility. Being within the historic district scenic resource zone, there were height restrictions based on these view corridors from the park. These had to be considered when thinking about exterior improvements, such as adding the exterior salt tank or adding a hopper to the roof of the facility. So in the end, the recommended solution ended up being to stick with the bulk sodium hypochlorite. By being thoughtful in the implementation, we were able to adhere to the AWWA best management practices. The amount of storage that is being provided will allow the Water Bureau to receive bulk shipments when it is necessary. For example, when they're initially boosting the reflecting pools. But then in their day-to-day operations, the demands are most likely not going to warrant a bulk delivery. So they would be able to get a mini bulk delivery and then dilute it. So we put in the infrastructure for operations to be able to dilute the deliveries that they get, such that the hypo will degrade that 7 times slower that we talked about earlier. And then with this, there's a little less capacity than their current system, but much more room within the footprint of the building for operations to work in the facility. And so with that, we move forward with designing the facility, and it'll be going into construction prior to the reflecting pools being online in 2024. And I don't know where we are with time, but if anyone has any questions for Juanita or myself, we'd be happy to answer them.
Thanks, Amanda and Juanita. If you have any questions, please type them into the Q&A. Cheryl Capron did point out that Seattle had a very similar project on the Lincoln Reservoir, which was replaced 20 years ago, which was also a historic reservoir. And I guess she said that they found that when the reservoir was covered, booster disinfection wasn't really needed since there was less off-gassing and less demand for hypo. And so they ended up only using the hypo for the reflecting pool. So I guess the question that might come out of that is the impacts of covering the reservoir and maybe reduction in needed chlorine been analyzed as part of this project?
Juanita, I don't know.
Yeah, it's actually super interesting. They've been offline with these reservoirs for almost 6 years, I want to say, and keeping really, really good data for how it's affecting basically we have all these upper tanks that we pump to from Washington Park. And there are a few tanks for a few months of the year that hover and cover and go over the lines of the water quality, the performance, where we are expected to stay and where we would like to stay. So they do extensive flushing. They empty and clean tanks, and they have 2 different flushing programs they're operating. So they put a lot of operations budget and time into this and planning. So they hope that even if the reservoir itself doesn't have a higher demand for, have a degradation rate that, would increase the demand, they're still able to boost for those further reaches that are having water quality issues.
I see. Okay. So the boosting applies to not just the reservoir, but these other ongoing issues. That makes sense. Thank you.
Yeah, interestingly enough, the reservoir itself is probably not going to have any issues because it goes straight into the local pressure zones. It doesn't get pumped and have a long residence time once it leaves the reservoir. So we were flexible with the where we are installing the ports so that we can have a port that feeds the upper, the further out tanks with the longer residence times, and not even boost into the reservoir if we don't need to.
Makes sense. Thank you. Matt Hewitt asked for some elaboration on the staff concerns with bulk hypo. Like, what specifically were the concerns and how are they going to be dealing with that now that we're moving forward with bulk hypo?
I can grab this one. So bulk hypo at another facility, our groundwater system, ended up degrading and causing an issue with how to get rid of it. They had a couple of, because they have long periods of inactivity. So they were worried that this same thing might happen. As Amanda mentioned, we aren't really clear on how much chemical we're going to use, and it will vary throughout the year and throughout the seasons. So having all that chemical sitting there, is the bulk 5,000 gallons, something like that, and it might take us a month to get through that. So that was the concern, was having chemical to either burn off, overdosing the reflecting ponds, or diluting and not having the space to dilute it because the tanks are only just above 6,000 gallons. So we basically came up with the, they'll probably start with a bulk delivery, and then maybe they'll go straight to mini bulk in the, in the next shipment if they have an issue with that chemical. Does that answer the question?
Sure. And can you describe what you mean by mini bulk? Do you mean just like a tote delivery or something like that?
No, it's actually a truck that pumps it into the tanks. And I want to say, Amanda, do you remember how much it is? Is it 2,000 gallons?
Yeah, I can't remember offhand, but it basically was anything less than a full shipment.
I see.
Yeah, it could ultimately be a tote if they really aren't using that much. So,
but what you mean by mini bulk is just a smaller delivery, not a full delivery of an entire tanker truck or whatever.
mm-hmm.
Right.
Yeah.
Great. Thank you. That's all the questions we had. Any others out there lingering? Looks like not. So thank you both so much for presenting. We will take a short break and we'll restart our next two presentations at 9:50. So why doesn't everyone just take a little snack or rest or stretch break, and then we'll rejoin maybe a minute or two before 9:50. I'll kind of kick things back off. Thanks, everyone. Hey, Kim and Carrie, why don't we test out your audio, make sure everyone can hear you.
Hi, can you hear that?
Yes, I can. I can even see you.
Great. I was just testing my camera to make sure it worked. I'll turn it off because Kim will go first.
Okay, sounds good. But it is good to see the presenter's face. Thank you.
Morning.
Morning, Kim. I can hear you.
Oh, good. Woo! Can you see the slides?
I can. Yes, it's working.
Okay.
And we'll give folks just another minute or two, and then we'll kick things off here.
Yep, that's fine. I'll try to keep breathing.
So when we do a quick transition between Kim and I also will share my screen with slides. So once Kim's done, can I just click share screen to take over, or do you have to do something, Josh?
Nope, that'll be all you have to do. You just click your share screen. It should automatically take over. If it doesn't for some reason, we can have Kim stop her presentation, but it should be.
Yeah, I'll stop. That's fine.
All right, I think we're getting pretty close. We can kick things off here in just a moment. Before I kick things off, I want to give everyone a chance to do our next hour polls. So I think our hour 2 poll is going to be kicked off here. This hour presentations is focused quite a bit on ozone, and so I wanted to have a question just around taste and odor. So I'm going to launch it now. And it's basically just asking how concerned everyone is about the taste and odor of the water where you live. Just get a sense of who could benefit from something like ozone. We'll wait till we get everyone responding. Sounds like there were a few people that are having issues with their polls, and if that's the case, go ahead and just type your answer into the Zoom chat, and you can just send it directly to me and the panelists, or to everyone if you want. Up to you. It looks like we don't have quite everyone yet, but it looks like most folks are pretty lucky. About 45% say they're not concerned about the taste and odor of their water, whereas another 40% say it's a moderate concern, and then there's a small subset, looks like 5 folks have said that they're very concerned about the taste and odor in their water. Give folks another 30 seconds and then we'll close it out. All right, we'll end the polling there. And I'll share those results for those that are interested. You should be able to see those. So I'll move on to introducing our speakers. We have Kimberly Reed and Carrie Duncan with us for this Ozone Operations 101 presentation. Kim is the operations manager at the Willamette River Water Treatment Plant, serving the cities of Wilsonville and Sherwood, Oregon. Veolia has been the contract operator since the 15 MGD plant went into production in 2002. She helped pull together years of operational data for the Ozone Coalition submittal to the Oregon Health Authority for disinfection credit and pre-filtration ozone treatment. She has a master's in environmental engineering from Georgia Tech and has worked for the EPA and as a consulting engineer and as a homeschool mom. And Carrie Duncan is the water supply and treatment manager for the Lake Oswego Tigard Water Partnership and oversees operation and maintenance of the river intake and water treatment plant, as well as the water quality and water conservation programs. Carrie has a bachelor's in biology and environmental science from Willamette University and a master's in public administration and public policy and management from the University of Oregon, and has worked in the water profession for 20 years. All right, go ahead, Kim.
All right, good morning, everybody. I'm happy to be able to join you this morning. I will say that I am not an ozone treatment expert. So my goal here this morning is to just try to provide you some information with our system that's been in operation for over 18 years. The slide that you see is we actually are so lucky to have this beautiful park that is part of our total site for the plant. So the plant is behind the ivy colored wall, and throughout the park there is signage, which is the inset in the lower right hand corner, about the treatment processes that are going on behind the walls. And so the contact chambers for the ozone treatment system are there. I wanted to thank Delora Kerber, who is the Public Works Director for the City of Wilsonville, for her support of this presentation this morning. As stated in the intro, we are a 15 MGD plant right now, and we are in the beginning of the process to upgrade to 20 MGD. Let's see if I can get the slide to advance. There we go. Okay, so this morning we're going to cover a really brief system overview, the operational goals of our system, the maintenance, a little bit of the maintenance history and the costs, and future upgrades. So in particular about the maintenance, we do some preventive maintenance, and also the big ticket has been the corrective maintenance that we have done. And we had a 2017 master plan was written by Carollo, and so part of the upgrades were identified in that master plan. So the system components here, we have a PCI Wedeco system. Each generator is capable of 300 pounds per day. So we're going to see some photos here in a minute. So, but we have a liquid oxygen tank and evaporator system, the nitrogen boost system, 2 ozone generators, 2 8-chamber contactors with bubble diffusion in cells 1 and 2, ozone destruct system for the headspace, dissolved ozone residual destruct system, and then of course the instrumentation and safety fail-safes for, because ozone is acutely toxic, and then the PLCs. So here are some photos of our system. You'll notice on the right that our ozone generators, unlike a lot of the images that you see, are in these blue boxes. And so we'll talk a little bit about what's inside the blue boxes later in the presentation. The liquid oxygen tank is the photo there in the upper left-hand side. We have a 6,000-gallon tank. It is serviced by Messer, which formerly was Linde. And this equipment is leased, and so therefore it is maintained and automatically refilled by Messer. And then in the lower little photo there, that is our nitrogen boost system. So the overall production is more efficient in the presence of nitrogen. So really that's just an air compressor. Our two 300 pound per day Wedeco generators, we do run them one at a time, and they convert the oxygen into ozone. They are capable of doing that anywhere from 2.5% to 12% by weight. So they're very oversized really for what we need. So yes, we run one at a time. At our facility, we have these bubble diffuser discs, which is different than the side stream injection that you'll see at the Lake Oswego Tigard plant. We, even though we have the ability to run these in cells 1 or 2, cells or chambers 1 or 2. We do use just right now the chamber 1 for that. Each chamber, you can look at the photo on the right, which is the gallery. So the treatment chambers are to the right and the left there. So they're large, just concrete, rectangular concrete tanks. Each chamber is 6 to 10 feet with a water depth of 21 feet. So any ozone that's not dissolved ends up in the headspace. This gas is heated and it's run through the catalyst system, which converts the ozone back to oxygen before that gas is released to the atmosphere. The residual ozone in the water is quenched with calcium thiosulfate, which is, there's actually a vault there in that doorway. And so it's quenched before it flows onto the filters. We do maintain just a very slight residual ozone so that we know that we're dosing that chemical correctly. So initially, ozone was installed in this plant in order to address taste and odor concerns. However, we operate for the 1-log disinfection of cryptosporidium. So the chart from the EPA for the CTs required for that 1-log crypto disinfection is posted at each of the HMI workstations for the operators. And so they are manually, they're looking at that chart and then they're checking their dosing requirement based on that. So CTs are obviously, they're based on temperature and they are higher at colder water temperatures. Our operators adjust the dose set point in order to moderately exceed the CT, but in balance with addressing efficiency and cost concerns. So at the time for this screen was our ozone generator number 1 was running, and we were creating an ozone concentration of 2.8% by weight. So if you look at the screen, there's it kind of towards the top middle there, you can see the ozone dose set point of 1.26. And so that's the control that our operators have over the system. We use both contact trains always, and the detention time, depending upon obviously the flow, is 45 minutes in the winter to more like 15 minutes in the summer. So the CT varies from 17, once again in the winter, to about 4. And our applied ozone concentration is about 0.5 milligrams per liter. So to calculate the CTs, this is actually done in our SCADA system. Now, the way that this is presented on the slide here is, it's not really the most intuitive way to calculate CT, at least I don't think so, but this is the actual logic programmed into the PLC. So the CT is calculated for each train, and that's what displays on the SCADA. The CT shown in the center of this graphic here is just for train 1 only. The total plant flow is halved, and the assumption being that this flow is equally, the flow is equally split in the inlet channel. So note also in the little graphic inset that the concentration for chamber 3 is a little higher than it is for chamber 2. The water temperatures in the middle of the 3 yellow boxes, they're at 11.6 degrees centigrade. So this is a screenshot from March 12th. And the colder water temperature requires longer for the ozone to dissolve. We've observed that when the temperatures are especially low at about 5 to 8 degrees centigrade, the concentration of dissolved ozone can actually be highest at the last sample point in chamber 8. So note that the weighted concentration calculation relies upon decreasing concentration through the reactor cells because we're heavily weighted towards that last monitor. If we were to convert to using ozone for disinfection credit, the logic statement would, a logic statement would need to be added to switch this weighted concentration calculation. So even though we've been submitting the ozone CTs with the monthly report to OHA, we currently meet our required disinfection CT with chlorine in our clear well alone. There has been no regulatory review of this approach with OHA, so just wanted to be clear about that. So we are creating documentation with consistent performance from our ozone system, and for the hoped eventuality that we would be eventually approved for pre-filtration ozone disinfection credit. So on our SCADA, we have a number of trends that the operators are able to easily access. In this 16-hour trend, you can see the variability in the CT, which is based primarily on flow. So the CT is that orange kind of line at the top. So compared to our 2.9 million gallon quiescent clear well, the flow through the ozone contact chambers is pretty dynamic. So by accessing this trend in just one click, the operators can see the direction of the CTs and make small adjustments as needed in order to really be on top of this dynamic system. So we have received, or the city has received back, a letter from OHA of what their requirements would be in order for us to be able to operate or get disinfection credit from our ozone system. So these include the 4 of the bullets that are there on your screen. So this plant has the active flow ballasted coagulation flocculation process. The operational target for us for settled water turbidity is 1 NTU. After more intense rainfall events, when the influent turbidity may exceed 40 NTU, we have seen settled water turbidity values around 2 NTU, but since 2013, we have only once come close to approaching the 5 NTU requirement that OHA would impose. So their second requirement there about the Giardia inactivation, well, we currently dose for the much higher 1 log inactivation of crypto, so that's not a problem for us. The third bullet there on the effluent turbidity requirement, well, under contract with the city, we require a filter effluent turbidity of less than 0.1 NTU. So each month, along with this required report to the state, you know, we're consistently meeting the 0.1 NTU. So we have done some pretty major maintenance on our system here. So there's a lot that goes on inside that blue box that you saw in the photo earlier in the slide presentation. So the incoming power is 480 volt, and it is converted through several steps into direct DC power, which is run through the electrodes in the dielectrics. The digital control modules, the heat sinks, and the PLCs have all been replaced in the 18+ years. All of the original equipment for the ambient and process gas phase monitors were replaced 2 years ago. So here's some photos of what's inside the blue box. We do have 3 cells in each generator. Here you see 2 that are open. So by far, the biggest challenge, the biggest repair challenge so far was the failure of the welds in the original pressure vessels, these tubes, these columns. And what happened when the welds failed was that nitric acid pooled in the cabinets. Harris Thermal Products to the rescue for us, which they are located in Newburgh, which turned out to be really wonderful. They constructed the new heavier pressure vessels. The flanges were larger, so on the left there's a photo of them constructing kind of a bump out on the back of the cabinet. The cooling water piping also needed to be rebuilt because of the new the larger vessels. Each of those vessels there has 253 dielectrics, all of which were replaced. They needed to be tested individually, and then row by row they were cross-linked and tested again. Our O&M lead operator here, Shane Wire, he was working with other operators and a Xylem technician, and it took weeks to get these rebuilt. An unexpected problem was that the metal tubes had to be perfectly straight, which seems kind of obvious, but we did have an issue with when inserting the glass tubes that they were breaking because the metal tubes weren't straight enough. So we got that taken care of too. So over the 18 years, I estimate that our total repair costs were about $300,000 on the entire system. This cost would have been much higher if the rebuild of those generators with the new vessels had not been accomplished in-house with Veolia staff and the locally sourced pressure vessels, because Harris Thermal was back and forth here quite a bit helping us out. That's been one of our major issues, is that there are no qualified Wedeco technicians who live locally or even on the West Coast, last I checked. So bringing in a manufacturer's technician for repairs must be scheduled weeks in advance, and costs include airfare, lodging, and meals. We also ended up replacing the gas phase analyzers in 2017 with Teledyne units, and those cost $6,000 each plus installation. Our ongoing operating costs are on this slide. So interestingly, most ozone usage is about, monthly ozone usage is about evenly balanced. The rise in flow during the summer is offset by the drop in ozone concentration required to meet CT. So daily demand in winter is about 145 gallons of LOX per day. Our flow demand at that point is about 3.5 to 4 MGD. Whereas the number for LOX in the summer is about 165 gallons per day. So just 20 gallons a day more. It's not really a big difference. So the cost there is about $200 a day. Power usage, I was actually kind of surprised when I looked at this. So the power usage just to run the generators is about $10 to $30 per day for 40 kilowatt hours per million gallons. So pretty reasonable. We spend a lot more money in pumping water around than we do on the ozone generation. So unlike pumps and motors, finding experts to service this equipment once again is difficult. and on the East Coast. So cost includes travel expenses. Our gas phase analyzers, the annual calibration is performed by GSO3 Services. Gary's out of North Carolina and he travels the West Coast, so we snag him when he's over here. And that cost is about $3,800 to $5,000, including the travel. We do calibration of our Rosemount liquid phase ozone analyzers in-house. So upgrades. What we have found is that the LOX delivery tankers have gotten bigger since our plant was designed over 20 years ago. And you can see the orientation of the tank to the building, and the truck driver needs to back into that space in order to offload the LOX. It's tight. He hasn't hit the building yet, but I can't watch when they're here. It makes me nervous. So the concrete contact chambers in the upper right-hand corner. So the bubbles in the flow are very dynamic, and of course we can't see in. I wish we had a plexiglass window there so we could see what's going on. The sample water is fed into the analyzers with 1/2-inch stainless steel tubing. We can select cells 2, 3, 7, or 8. We currently sample the bottom of cell 2, the top of cell 3, and the top of cell 8. It'd be interesting to be able to switch that up and see what differences we got. And lastly, like you saw, our generators here are blue boxes. We have alarms, of course, on the outputs and tags in our SCADA system to monitor the cooling water temperature. And the units will alarm if something fails, but there's not really any good testing protocol that we have found to be able to determine the condition of the equipment, especially now that it's 18.5 years old. According to Xylem, who's the WTC representative, some of the components in our ozone generators are obsolete. So we're just playing a waiting game for the next alarm and find out if the generator can be brought back into service or not. Thank you for your time. I can be reached at kim.reed@veolia.com, and I will turn it over to Carrie.
And Carrie, I know that you're coming up on your time here. We can give you up to like 5.
Oh, I'm sorry. Gosh.
We can give you up to like 5 extra minutes if you want. And I don't know if you're talking, but we can't hear you, Carrie.
Thank you for that. I appreciate it. I'll walk through this quickly though, because I know we're close on time. And I will try to get this going correctly.
Once you're in the presentation, but you can always swap which screen is being shared. Go to the swap screen option.
Which one are you seeing?
I'm currently just seeing an open PowerPoint with all the thumbnails on the left.
Got it. Okay, let's try this again. How about that?
There you go.
Okay, so
go to this. I don't know. It's still go to display settings on the top, and go to swap presenter and slideshow view.
There we go. Thank you.
That's good.
All right. So we saw a view of the Wilsonville treatment plant. I'm just going to give you a view of the Lake Oswego Tigard water treatment plant ozone system, and we'll move pretty quickly. We're a 38 million gallon a day plant with high rate ballasted flocculation, intermediate ozone, and biologically active GAC filters. We serve 100,000 residents in Lake Oswego and Tigard. We were completed in 2017, so we're a fairly new plant. We chose ozone. We don't use it currently for disinfection, but we chose ozone really as a kind of a future insurance policy for our system. This was a large capital project, $250 million for basically a new backbone in our water system, including a treatment plant. We were investing for our future. We wanted ozone for taste and odor control, treatment and biological filter optimization, disinfection byproduct control, and also kind of a look at emerging contaminants such as hazardous algal blooms, herbicides and pesticides, pharmaceuticals and endocrine disruptors. Our system is a side stream injection ozone system. So in contrast to the bubble diffusion that Kim showed you, we have the same front of our system. I'm going to see if I can use a laser pointer here. There we go. So same liquid oxygen, nitrogen boost system is the same, although different size, some different brands of ozone systems you'll see. We have 2 ozone generators rated at 560 pounds per day and cooling water skids to keep those systems cool. The difference is the side stream injection skid. Rather than bubbling ozone directly into a contact basin, we take a side stream of plant water, inject that ozone into that side stream, and then inject that concentrated ozonated water into an ozone contact basin through a flash reactor. Interesting. It doesn't want me to move with the laser pointer on. All right, so this is a picture of our LOX tank. It looks the same as the Wilsonville tank. One difference is that we do own our LOX tank. And so we purchase on the market. We tend to have contracts with LOX providers. We also have a maintenance contract with Praxair for maintenance of this tank. Quick ozone chemistry. Ozone is created by taking your oxygen molecule, breaking it up with electricity. You create the free oxygen molecule, and then that binds to the O2 to create O3. There's a picture of the ozone generator system, the dielectrics, which you saw from Kim's presentation, and then cooling water on the outside of the dielectrics and the electrical voltage in here. This is a picture of our ozone generators. We have 560 pound per day Mitsubishi generators. We have 2 of them. These generators produce up to a 12% concentrated ozone gas. And we typically run around 10% for optimum efficiency and performance in our system, although we can go up to 12%. There's a picture of our cooling water skids, pretty complicated, but keeping the ozone generators cool. And then an ozone destruct system. So ozone destruct, like you saw from Kim's presentation, will destroy extra off gas from the contactor headspace. And you take that, you heat it up, you go through a manganese oxide catalyst, and that'll destroy additional ozone. Here's a picture of our destruct system and that manganese oxide catalyst. So on to side stream injection, and this is where we are a little different from Wilsonville. These are our side stream injection pumps. So once we've created that ozone, which you saw from the generators, we're piping that ozone gas into our injection room. And then these pumps are pulling off a side stream of our plant settled water off of our settling system. And they're pumping it into this ozone injection skid. Here's a side view of that ozone injection skid. Ozone gas is coming in. Let's go back to my laser pointer. Ozone gas is coming in from here, from the left. It's controlled through an ozone flow control valve. And then it goes into this injector, ozone gas injector. The side stream of water comes down here and flows in, and so this is where you're injecting your ozone gas into the ozone, into the water. I wanted to note here, material compatibility is very important. One challenge we've had with our system, we did specify the correct materials in our contract documents. Seals, ozone likes to eat away everything. So stainless steel is essential. PTFE for seals and gaskets is essential, and it doesn't automatically come with things like these flow control valves and other items. So although we specified that PTFE should be in all these, they weren't. These were details that just didn't happen. And so after about 6 to 8 months of operation, we started getting leaks and learned that, you know, these internal components were not correct. So we had to rebuild all of these little gaskets and everything. That was not fun. So make sure all your components, everything, and contact with ozone is compatible. Okay. Ozone analyzers are critical to the system. These are ambient ozone analyzers, oxygen analyzers. This is a handheld analyzer. This is really important for detecting leaks. We have a monthly preventative maintenance item where we take this little analyzer and we go through every part of our system to look for leaks. And that's a really critical part of our operation. Also, maintenance of these instruments, everything, the oxygen analyzer, the ozone off-gas analyzers are also critical, because if any of these instruments are not functioning, you know, our system, it has interlocks to shut down, because these are critical safety items. So these PMs are really important to us. This is our side stream injection system. This is a MASI injector. So we're taking the ozonated water, the side stream, and injecting it into this, and then we get the full plant flow, and that is put into our ozone contact basin. Then a picture of our ozone contact, or a diagram of our ozone contact basin. We measure ozone in the water at each of these numbered points, 1 through 5. We inject calcium thiosulfate to remove the ozone at the end, and then we will measure the last at number 5 to make sure that we've removed all that ozone. We have found that an ozone analyzer that does not typically measure ozone, so number 5 is usually in 0 milligrams per liter of ozone, it'll go dead. And it needs to be in the presence of ozone to really stay fresh and functioning. So we actually take this ozone analyzer and we rotate it with one of these earlier spots very frequently, almost weekly, in order to recharge that point, so that we know this is functioning, so that if we did get any ozone past our ozone quench, we would be able to measure that immediately. Some maintenance items. We have, in 2019, we had 153 work orders for our ozone system. The majority of our work orders are for instrument calibrations, leak checks, and valve maintenance so far. We haven't had any major rebuilds like Kim showed to you, but that's because we have a new system. We also have a service contract in place for LOX maintenance. And some overall costs for our ozone production. So our plant is rated at 38 million gallons a day. We range between 10 to about 24 million gallons a day of water production. And with an ozone dose of about 0.6 to 0.8 milligrams per liter, here's some of our costs. LOX, about $19,000 a year. Electricity, this is estimated about $10,000 a year. Calcium thiosulfate, $23,000 a year. That's to remove the ozone. And so then our total costs, we think, are around $51,000. So about $12.70 is the ozone cost per million gallons of water produced. Something important to note here is the calcium thiosulfate cost, that could be lowered if we were, our ozone system is a little bit oversized for our low water production times. So if we were able to reduce this ozone dose, let's say down to 0.4 or 0.3, and just produce ozone for the water demand, and we wouldn't have to quench so much, we could save a lot of money. Right now, though, we can't do that in the wintertime when we have low demands. Our system just won't turn down that low. So sizing is important, and it can save money in the long run, but can also cost money at the build. I'm going to stop there. It was kind of a quick whirlwind, but I don't know if there's time for questions, but that's the end of my presentation.
Thanks, Carrie. Looks like we had 2 questions. We'll go through them very quickly. OHA, there's a comment from Jay McPherson at OHA. It said, and this is for Kim, that the drinking water program at OHA grants the waiver if the conditions are met. So I guess the question was, has the plant applied for getting a waiver and getting the log credit through the ozone system, or is that in progress? What's the timing on that looking like?
So can you hear me?
Yes.
Okay. So my understanding that, and this is the city's intent, is that as part of the 20 MGD package for upgrading the plant, that the ozone might be a component in that. So we have consulting engineers on board, and they're working with the city to make determinations about that.
Okay. And then the other question was also from Jay, if Viton seals were considered in addition to Teflon when you're looking at the seals and replacing them.
I believe Viton may have been one in the list of seal material that we looked at. And I don't know if they were available for this particular valve. What we ended up with was that, yeah, the Teflon, the PTFE was the kind of the material that was available and that would work for this particular application. And that would be long lasting.
Okay. Thank you both so much for your presentation. We'll move on now to Nicole Williams and Rob Keller. So Nicole and Rob, you should be able to unmute yourselves and share your screen whenever you're ready.
Hello. So let me see if I can share my screen here.
I can see both. Yeah, that's a good start.
How about that?
Yes, looks good.
All right. My name is Nicole Williams. I am with Corlo Engineers, and I'm going to be co-presenting with Rob Keller from the City of Salem.
Let me introduce you guys real quick. Just wanted to make sure we're set up first. So,
sure.
I'm sure you were just going to introduce yourself, but I'll
sure was, but yeah, go for it.
Take it away from you. Nicole is currently the resident engineer overseeing construction of a new ozone treatment system at the City of Salem, Garin Island Water Treatment Plant. For the past 5 years, she has participated in various stages of drinking water treatment plant design with an emphasis in ozone and biological filtration processes. Nicole joined the Corlo Engineers in 2015 after graduating with a master's degree in civil and environmental engineering from Brigham Young University. Rob is a project manager with the City of Salem. During his 4 years with the city, he has managed projects in water distribution, sanitary sewer collection and conveyance, storm sewer conveyance, and treatment, and is currently aiding in the city's water treatment efforts, including ozone. Prior to coming to the city, he worked for the Idaho Department of Water Resources and received his Bachelor of Science in Civil Engineering from South Dakota School of Mines and Technology. And I know you guys are starting a little late. Go ahead, and if you need all the time till 11:10, I think that's okay. So you take it away.
All right, thank you
By
very much.
11:10, I meant 11 o'clock, sorry.
That's great, thanks Josh. So like I said, Nicole, like Josh just said, Nicole Williams, Corlo Engineers, and Rob's with the City of Salem. And we're gonna be presenting on the evolution of cyanotoxins for the City of Salem. I'm sure many of you on the call are familiar with the water quality challenges that Salem experienced during 2018. But a quick thank you to all of the many people that pulled together to help out during that event. It truly was a team effort, and it was really cool to witness. And so what we're going to do is we're going to talk a little bit about the background of the project, kind of give you an idea of the water treatment plant that we're looking at. And Rob Keller is going to take that and he'll talk to you about the near-term solutions that we came up with and the long-term solutions that are in the works. And then I'll jump back in and I'll talk about some pilot testing that we did last summer and give a project update on where we are right now. So take it away, Rob.
All right, let's see if I can grab controls from Nicole here.
There you go.
All right, I'd like to start by going over a little bit of the background for the city of Salem. Just talk about our current water source. It is the Santiam River, and it's a pretty pristine source. It's very clean water coming from Jefferson Mountain. There's a couple of impoundments on it, but historically very pristine water, low turbidity, low TOC. And what this ultimately means for us is that our water source doesn't need a whole lot of treatment prior to us putting it into the distribution system. So I'll go over actually what our treatment facility looks like and our process. So as I said, we get water off of the Santiam River, and if we have good quality water, a low turbidity water, we can actually go through just a single stage filtration using our biological filters, these slow sand filters. From there, a low dose of chlorine and some pH adjustment, and it can be sent off to our the people of Salem. If we have a high turbidity event, currently what we would do is use one set of our filters as a roughing filter, and then using a caisson pump station, relift that water and send it through a finished filter, the same slow sand filters using biological treatment, and then again, the chlorine and pH adjustment before it gets sent on to the city of Salem. So the issue that we had in 2018 is due to this treatment, we had an issue with where we encountered some cyanotoxins. And because there's not a lot of treatment that we currently had to do, what ended up happening was we had cyanotoxins break through our filters and enter the distribution system. So on May of that year, we had to issue a do not drink advisory due to the level of cyanotoxins being above the recommended limit for vulnerable population. So we issued a do not drink order at that time, and then the cyanotoxin level dropped down for it to come back up again later in the season, where we had to issue a second do not drink notice, which stayed in effect until later in the season, July 3rd to be exact. So then we had to determine what were we going to do to combat these cyanotoxins. So using our current system, we had a couple of different approaches that we could do. We could avoid the cyanotoxins by using our ASR system or by using the groundwater that we have in our system. But between those two devices, we only can sustain the city of Salem for 2 to 3 days in a row. So it really was not a viable solution for avoidance. The other thing we could do is we could dilute the water using groundwater, but we found with our slow sand filters, diluting the water can be an issue. Due to that low TOC that I talked about earlier, when we dilute with groundwater, it's actually bad for our filters. The biological part of it dies because of not having enough food to consume. And then the other choice would be to extend our free chlorine oxidation, which at the time just wasn't enough to actually combat the cyanotoxins. So because of that, we had to have a quick and immediate response to try and address the situation. Luckily, we already had Corolla working with us on our groundwater blending. So the city and Corolla was able to deploy a team rather quickly to try and determine how we can address the situation. We took a measured approach, decided that we would do powder activated carbon to try and address the situation. And we started by doing a phased approach, bench scale testing, some pilot testing, and ultimately moving into full scale implementation. Thankfully, it only took us about 3 weeks from when we started doing our bench testing to where we were able to implement the powder activated carbon system. In starting that powder activated carbon system, we did know that there were some risks that we would have to deal with. Given the low turbidity that we see in our water, our filters cannot handle a whole lot of solids load. So putting that powder activated carbon into our system, we knew we would have an issue with maintenance where we would end up plugging and clogging our filters. So that was one issue we needed to address when we started looking at the powder activated carbon. The other thing we knew is because of that low TOC from our source water, we knew the powder activated carbon would take some of that away. So we needed to find an alternative source of carbon to give our filters to ensure that they had enough food for the biology. So here is that treatment train that we showed earlier, just showing where we implemented the powder activated carbon. So the powder activated carbon we implemented after we took in our source water prior to roughing filters. We utilized those roughing filters to settle out the powder activated carbon before sending them on to finished filters. As I just said, we needed to supplement a new source of carbon, so we added acetic acid just downstream of our caisson and pump station to make sure that there was enough food for the finished filters. Using our current chlorine system, we elevated our chlorine levels, which required us to put in a dechlorination facility prior to us, to the first users in the system. So that was the near-term solution that we were able to come across with, but we knew that it was not really sustainable. So we had to also at the same time look at a long-term process that we would implement into our treatment. We looked at just doing powder activated carbon in the long term. However, it's very messy, labor intensive, and our operators really do not like it. So we tried to steer away from that. We looked at the hyperchlorination, and while that is a good solution, we didn't feel that it was enough, but we would have to do something else as well. We also looked at granular activated carbon. However, given the island that we used for the treatment, there really wasn't a big enough footprint for that. We also looked at UV, and the drawbacks with that were a lot of power consumption and just how we would implement it into our current process. And we also looked at ozone oxidation and finally decided to move forward with ozone. In addition to that, we also started investigating trying to find more groundwater sources so that we could blend the water if we had a high cyanotoxin event. So as I said, the recommendation was ozone, and this is just showing that same treatment train again, but showing it with where we're going to put in the ozone system. So you can see that there's no longer powder activated carbon in front of our roughing filters. However, we're still using those roughing filters, and then after the caisson, we're going to implement the ozone injection, as well as adding some additional groundwater sources through rainy well collection. We will still need the acetic acid, which Nicole will talk about a little bit, and we're still going to use hyperchlorination, so the dechlorination facility is still needed. So we knew that we'd have to take a pretty quick approach, but we wanted to make sure we weren't being too hasty or making the wrong decisions. So before we moved forward with doing the full design and implementation, we wanted to make sure that we had a peer review of what Carollo had studied, just to make sure the recommendations were agreed to. So we did that peer review at the same time that we were selecting our design consultants, and Black & Veatch did that review and agreed with Carollo's recommendations to implement intermediate ozone. And what the other point of this slide is to show that during that that measured approach, we knew that while we're implementing ozone, we would still have to go through 2 cyanotoxin seasons prior to being able to implement the new treatments. So we'd have to use those near-term treatments that I talked about earlier. And then finally, I wanted to show that we knew we were going through 2 seasons of cyanotoxins, and this shows the 2019 cyanotoxin season and how high the actual levels were coming into our treatment system. However, if you look at the bottom of the graph, that is Aldersgate. It is our first point where we distribute water out of our system, and you can see that we didn't have a single event where it actually got into our distribution system. So this just shows that our near term has been working while we wait for the implementation of ozone. And with that, I will give it over to Nicole.
All right, thanks, Rob. So like Rob said, the city selected ozone as their long-term solution. And we just had, some questions about how is the ozone going to interact with the existing slow sand filters, these biological filters that the city already uses. And so we decided to take advantage of the opportunity that we had last year to do some pilot testing during the summer. And so what you can see here on the left is this is the ozone pilot system that we rented from Intuitech that can actually generate ozone on site. And what you see here are 2 ozone contactors where the ozone is able to interact with the water. And we use their existing slow sand pilot filters, and these are 4-foot diameter, 10-foot tall slow sand filters that mimic the ones that the site already has, that the plant already has. And so this is a spoiler alert. This is probably the most important slide that I'm going to talk about, that just I'm going to run through really quickly the questions that we had and the answers that we found. So the first big question that we had is ozone going to work? That's the entire driver for this project. We just wanted to make sure that ozone was indeed going to oxidize and remove these cyanotoxins. And so we found that yes, can it effectively remove cyanotoxins? It can. So that was great news, just gave us some confidence. The second question we had is carbon going to be a necessary supplement downstream of ozone? So Rob talked about how when the plant's operating in 2-stage filtration, their water is just so clean, so low TOC, that the first filter basically removes all of the organic carbon in the water. And so there's nothing left to sustain the biological filters on the 2nd-stage filters. And so they're adding a supplement, a carbon supplement. And so the question is, we know that ozone can take big chunks of total organic carbon and break it down into smaller bite-sized pieces. And the question was, is a carbon supplement still going to be necessary when they're operating with ozone? And the answer is, unfortunately, yes. For the Guerin Island project, they will still need a carbon supplement. The next question we had, can peroxide improve filter hygiene? We found that yes, it can, and I'll speak a little bit more on that later. Can the filter survive an accidental overfeeding of different chemicals? We're looking at adding ozone, hydrogen peroxide. What would happen if some of these chemicals were accidentally introduced to the biological filters? Would they still survive? And we found that yes, they can survive an overfeeding of ozone and hydrogen peroxide at low doses. And finally, we looked at some filter clogging algae events that the plant was experiencing. In addition to cyanotoxin producing algae, they also have filter clogging algae, which creates some challenges operationally. Do any of these new tools that we have help address these issues? And so we looked at that and found that no, ozone doesn't really help. Neither does hydrogen peroxide, but groundwater blending can. So we'll dive in a little bit more into some of these. So here's what we have. We have a few different treatment trains. And this is for the pilot specifically. And so we actually tested groundwater, and we spent some time testing pre-ozone, but I'm going to talk and focus mostly on intermediate ozone just because those had the most interesting results, and that's ultimately what the city selected for their full-scale plant. And so we have raw surface water that we pump onto a first stage roughing filter that's then ozonated and pumped again back onto the second stage filter, and we have an acetic acid supplement there. So that's the first train. And the second train that we looked at was the pre-ozone, where we have surface water that goes through ozone and then is sent onto their polishing their filters. And this is the pre-ozone that we didn't really experience any challenges with. We didn't see excessive head loss, so that was encouraging. But I'll talk a little bit more about this intermediate ozone step. So one of the big questions we had was, can ozonated filtered water sustain the second stage filters without the addition of any kind of acetic acid or carbon supplement? So what we have here on this plot is we have head loss on the left, and head loss is a metric for filter performance. If it's accumulating some head loss and you don't see any kind of total coliform or E. coli coming through, that means that your filters are performing well. So this blue line is our data from our pilot for the ozonated filtered water that was receiving ozone and being pumped onto a second stage filter. And over here on the right side of this graph, this green line is our acetic acid dose. And we tested 3 different doses. We tested a 0.3 milligram per liter dose of acetic acid that we knew from current plant operations worked well to sustain the filters when they were operating in 2-stage filtration. And we tried stepping it down to a lower dose, and we also tried no acetic acid. And what you can see happened is the filters were able to perform well and continue to accumulate some head loss at this lower dose and at the higher dose. But when we dropped off the acetic acid, we saw a dramatic drop in head loss. And down here, this graph is the same time scale as the one above it. And it's showing total coliform on the y-axis. And after that loss of acetic acid, we saw some total coliform breakthrough. So what does this indicate to us? It really just tells us that the filters weren't performing well. The drop in head loss and the total coliform breakthrough after the loss of the carbon source indicate that it does indeed need a carbon source, even with the ozone. So another thing that we looked at was hydrogen peroxide. And the real concern here is we have gone to all of this work to remove any kind of cyanobacteria or cyanotoxins that may be in the water with our intermediate ozone. The last thing that we want is we have the second stage filters are 5 acres, they're open to the atmosphere, open to sunlight. We don't want to literally be growing algae on these second stage filters that are producing cyanobacteria and cyanotoxins. And so we looked at potentially using hydrogen peroxide to mitigate any kind of algae growth on the filter surface and just keep them performing well. So these graphs are very similar to the ones that you saw on the last slide. Only here, instead of acetic acid, this is hydrogen peroxide. So there's a few different ways you can dose hydrogen peroxide. And the first way we tried it was a fairly large dose. And you can see that the head loss here on this filter that was receiving ozonated surface water dropped after it got this large dose of hydrogen peroxide. And that's not necessarily what we intended. We, in essence, chemically scraped our filter. And so we thought maybe we overdid it a little bit. And so we pulled off and tried a couple of smaller periodic doses around 0.5 milligrams per liter of hydrogen peroxide. As you can see, we didn't have any kind of total coliform breakthrough, and our head loss was about constant. It didn't drop, but it also wasn't increasing, which was encouraging to us that it wasn't growing any kind of algae on the surface, and we were able to mitigate any kind of biogrowth that may be on top of that filter. So 3.5 milligrams per liter reduced head loss accumulation, which was too much, but the periodic dose of 0.5 milligrams per liter seemed like a more reasonable strategy for them to keep good filter performance. So we also looked at overdosing ozone at the very end of the project to see what would happen. And so we intentionally cranked up the dial on the ozone generator to the point that we were able to measure a 2 milligram per liter ozone residual falling onto these slow sand filters, which required a dose around 8 milligrams per liter in order to get to get that high of a residual onto the filters. And this is the day that we did it. That's outlined in that dashed line on August 31st. And as you can see, there was no impact on filter performance. Did the biology on top of the filter actually see ozone? We don't know. The slow sand filters are very slow, and there's about a 3-foot head of water that's on top of these filters. And so it's possible that all of the ozone off-gassed before it actually reached it. But this was encouraging for us that if we were intentionally trying to overdose ozone to the filters and were unable to do it, that it would be difficult for operations to do it full scale. And we repeated that with hydrogen peroxide and found similar results. So finally, at the end of the test, we also wanted to challenge these filters. We worked with Dr. Robin Collins from the University of New Hampshire, who sent us some inactivated E. coli that we could use to spike the filters with E. coli and measure the true log removal that they were able to remove. And so what you can see on this graph is log removal of E. coli on the y-axis. And we have a control filter, which is the normal plant operations of just surface water. And we also have our ozonated surface water pilot here. And what we were able to see when we spiked to both of these pilot filters, E. coli, is we saw that both of them were able to achieve about 4 log removal of E. coli. And the Oregon Health Authority only allows a 2 log removal credit for slow sand filters. And so both of these were exceeding that allowable credit. And the ozonated surface water actually outperformed the control regular surface water filter. So this gave us some confidence that there aren't going to be any kind of issues with introducing an ozone process to a biological filter plant, and that the biological filters can still perform well even with ozone. And finally, we wanted to take advantage of the fact that we had this pilot out at the site during one of their filter clogging algae events to see if either the hydrogen peroxide or the ozone or any of the other new tools that we had might help them combat this filter clogging event. And so what you can see here on this graph is head loss again in the left, and our green line here is the ozonated surface water that we had a fairly high dose of ozone on, and the control filter with just normal raw surface water is in purple, and both accumulated head loss at about the same rate. So what this tells us is even if the ozone was able to kill the algae, it was not strong enough to oxidize the algae, the dead algae bodies that were clogging the filter. So unfortunately, that didn't seem to be a good solution. And we repeated the test with hydrogen peroxide and found the same results. It just wasn't strong enough to oxidize the filter clogging algae. And so finally, we tried groundwater blending. And so what you can see here is the same head loss on the left, but this blue line is now our ozonated surface water filter. So this is operating kind of as our control, and we had to scrape it here. And this is where we were blending groundwater and surface water at a 50-50 blend. So even though our control was accumulating head loss very rapidly, our blend of groundwater and surface water accumulated it much more slowly. So this gave us some confidence that pursuing groundwater is a good solution for the plant to help mitigate any kind of these future filter clogging algae events that they may have. So in conclusion, major takeaways for us from this pilot study were that 2-stage filtration with intermediate ozone does indeed oxidize algal toxins, which is great. That groundwater blending can help control any kind of filter clogging algae that they may have in the future. And so that would be a great option for the city to pursue. And finally, just that pilot validation gave us some confidence that these 2 technologies that we were looking into were going to work well for the plant and were the right solution for them at this time. And so just a quick update on where we are currently with the project. I'm actually presenting here from the job site trailer. And we are working on building an intermediate ozone plant. So here's the layout of the plant. The operators, when they first saw this graphic, actually laughed because the new buildings that we're planning on building are so small in comparison to their 5-acre filters. But we have some ozone generators that are in an ozone building, and then they're going to use a side stream process to inject that with an ozone contactor. And some new electrical buildings and some locks facilities to help with that. And we broke ground for this project April of this year, and we plan to have the ozone system online April of 2021. So it's a very fast-tracked, aggressive schedule. And the city also, like Rob mentioned, decided to pursue groundwater addition. And so they're going to start building some new groundwater wells. Testing is actually ongoing right now, and they're going to plan to kick that project off next summer with it finished in April 2022. And here's just a couple of photos for fun. We are actually pouring today the roof of this ozone contactor, and what you can see here in this photo is when they were pouring one of the last walls. And here they're putting in place the 60-inch effluent pipe from the ozone contactor. So it's been a great project to be a part of, and it's been a lot of fun to see this project evolve over the last few years. So with that, we'll open it up. I think we have a couple minutes left if anybody has any questions.
Yeah, thanks, Nicole, and thanks, Rob. Anyone have any questions? Feel free to type them into the Q&A. It looks like we have one from Al Vetrovs. He's asking, are there any finished water quality adjustments prior to distribution system needed with whether you're using groundwater or not? In other words, do you have to adjust pH or do something different to make sure your distribution water quality is maintained when you're blending?
Rob, feel free to jump in here if you have some additional insights. So the city normally in their operation, I don't believe they operate with 100% groundwater. Any kind of blending that they do is usually, they try to avoid going over a 30% blend of groundwater and surface water, just because they have experienced challenges in the past keeping those flow sand filters happy during at higher blends, and they always are adjusting pH. And so perhaps they have to have a little bit more of a pH adjustment to hit their target level, but I don't think that they necessarily attribute that to different doses of groundwater. Rob, any other thoughts for me there?
No, I don't think so. Like you said, currently we haven't done anything more than 30 just because our current system will not allow that. And we have measures in place to be able to dose both the chlorine and the pH adjustment. So if we needed to adjust that given our current analyzers, we would at that point. But we don't have to implement anything new for that groundwater addition.
Okay, thanks for answering. I also had a question surrounding the ozone dose. I mean, what kind of dose did you see was needed to get inactivation of the algal toxins?
That's a great question.
And I guess what's the design dose for the system?
That is a great question. So the maximum design dose, or the target dose, I believe, is 1 milligram per liter. And we tested, we mostly operated off a residual, a target ozone residual, just because when we were operating the pilot, we knew that any kind of fluctuations in influent organics could change the ozone demand. And so we targeted an ozone residual in the water to try to get rid of all of that noise. And we tested a 0.3 milligram per liter residual, a 0.8 milligram per liter residual, and like a 1.5 milligram per liter residual. And all of those were able to reduce algal toxins of microcystin below the detection limit from, I'd have to double check, but I want to say around 3, I don't remember, but they were able to reduce any kind of algal toxins from the influent levels that the plant was seeing to below the detection limit. Okay. So that gave us some confidence.
Good, thank you. All right, thank you both for your presentation. Just because we ran a little long with that last segment, I think we're just going to run right into our next presentation. So apologies for those that were expecting to have a nice break. Obviously, you can feel free to run and do what you need to do in a few minutes if you need to, but we'll just run and get started. Before we do, I had a quick poll just to kind of verify attendance for this last hour, so don't run quite yet, but I'm going to launch that poll now. And the poll is just asking, what kind of filters does your utility use for water treatment, as we get into talking more and more about different filters. We have surface water media filters, groundwater media filters, membranes, unfiltered system. If you are a utility that only has distribution and gets water from other folks, that would be a fine answer as well. And then other. So we'll see how folks respond. Give folks another 30 seconds or so. Looks like we have a good mix of folks. A lot of people with surface water media filters. Obviously, a lot of unfiltered. I think we have a lot of Portland folks on the phone, so that's where we're getting that from, among others. All right, thanks everyone for your participation in the poll. And I'll introduce Yone and Lynn. Can you guys try to talk and make sure we can hear you?
Can you hear me?
You might be on mute. Yone, I can hear you.
Can you hear me?
Yes, there you go.
I just need to figure out how to switch screens that I'm sharing, because when I played
that's
it,
the complicated part.
um,
PowerPoint sharing, you can always click on that display settings and it'll swap your screens for you if you click on the swap.
oh, okay, hold on, let me figure that out. So you're saying share this, and then...
There you go, that looks good.
Okay.
Right on my screen.
It's good on your screen?
Yep.
Okay, let me go back to the main first slide. Okay.
I'll introduce you guys in the meantime. So we have Yone Akagi is the water quality manager for the Portland Water Bureau and oversees the treatment pilot project. Yone has 25 years of experience in drinking water quality, although this is her first experience with a treatment pilot. So she's learning as she goes. Lynn Stevens is a principal engineer with Brown and Caldwell. She has broad and in-depth experience with drinking water treatment, including managing 8 pilot demonstration investigations, and she has worked with multiple communities from proof of concept through design and commissioning and ongoing operational support. Lynn is serving as the pilot study manager for the Portland Water Bureau's filtration project, which will be discussed today. Thank you both for joining us, and go ahead.
Great, thank you. I'm going to get started, and I think I'm actually going to turn off my video because I don't trust my connection to be able to handle this many things at once. And I don't have a cool background like Lynn does. So Lynn and I are going to be talking about the treatment pilot, and this is just part 1 of 2 presentations. Matt Gifford, my coworker, is going to be giving the second presentation. So Lynn and I are really going to focus on kind of the drivers for the new treatment plant and give a little bit of an overview of the, sorry, I'm trying to follow along here on my computer. Overview of the pilot plant. And then that's what I'm going to cover. And then Lynn is going to jump in and talk a little bit more about the logistics it took to set up the pilot plant and give an overview of the actual treatment train that we were piloting. Next slide, please, Lynn. So again, I'm going to kind of give an intro and talk about what brought us here in Portland to even need to be looking at a filtration plant and therefore a pilot study. And then Lynn's going to go into more details on what's going on inside of those blue and yellow boxes. Just a little bit of background on Portland system. The Portland water system serves almost 1 million people, including 19 wholesale customers. That's about 1/4 of the population of Oregon. We have an average day demand of 100 million gallons, and we have 2 excellent sources of water. So our primary source is the Bull Run watershed, which is an unfiltered surface water located about 26 miles east of Portland. And then we have a backup source, which is our Columbia South Shore well field. It's a groundwater well field. And we really use that groundwater well field when we need to either augment the Bull Run supply in the summertime, or as I mentioned, the Bull Run watershed supply is unfiltered. So that means that we can't serve the water if the turbidity exceeds 5 NTU. So that might happen if we have a storm or a landslide. And so when that happens, we can turn on our groundwater source and have that serve our customers. Next slide, please. So a little bit more about the Bull Run watershed. I mentioned that it's unfiltered. It's a protected watershed. So what that means is that there's no recreation, there's no people, there's no animals, there's no agriculture going on in the watershed. It's very protected. And so due to those protections and the high water quality that we have, and the low levels of crypto that we had, we presented this information to OHA along with public health information, and we were granted a treatment variance from the LT2, the long-term 2 enhanced surface water treatment rule, which had said that unfiltered water systems needed to treat for cryptosporidium. So with our variance, we were allowed to not treat for cryptosporidium, but we did have to keep testing the water and maintain all of our protections. So the variance was granted in 2012, And we were doing great under the variance for about 5 years. And then in the beginning of 2017, we started detecting crypto at low rates, but enough of it that it exceeded the threshold that was kind of set in our variance agreement. And it meant that we had to treat for cryptosporidium. So OHA revoked our variance and put us on a compliance schedule for treating for crypto. So just a little bit of, thank you, Lynn.
Sorry.
A little bit of background just on our current treatment process is, as I mentioned, the Bull Run, the watershed protection is really kind of our first line of defense there, starting off with really pure water. Then we do disinfect, and then the water flows to a second treatment plant where we add ammonia to form chloramines, and we also add sodium hydroxide to increase our pH, and so that's our corrosion control treatment. So we currently have 2 projects that we're working on, and the first is our improved corrosion control treatment project, where we're going to be adding CO2 and soda ash to increase the pH even further and to add alkalinity. That project is just started construction phase and is going to be online by April 2022. And then of course there's our filtration project, and that's going to be online in 2027. So both of these projects are being built to meet EPA regulations, and both of them have compliance schedules with OHA. Next slide, please. So why filtration? So when we realized we had to treat for cryptosporidium, we had a choice between building filtration or going with UV. And ultimately, the City of Portland and our City Council decided to go with filtration. And the reasons for that is that we felt it really would provide the best pathogen protection, and that's the whole reason we're building this, was for crypto, to deal with crypto. But we also felt like filtration would provide other benefits, such as reducing organic matters in our water and therefore reducing disinfection byproducts, which we thought would have significant public health benefits. I had mentioned that when we have high turbidity from storms or landslides, or if we were to have a fire, there would be high turbidity, which currently would shut down the Bull Run, but a filter plant would allow us to still be able to serve water. We just heard presentations about harmful algal blooms, and we thought a filtration plant, if that were to happen in Portland, a filtration plant would really position us well to deal with that. Also, as an unfiltered, we have sediment that enters into our distribution system through our water, and a filtration plant would limit that. And we really felt that the filtration plant would best position us to deal with future regulations and any emerging contaminants. Next slide, please. So I had just mentioned the sediments that enter into our distribution system. So I just wanted to talk for a second about another project that we have going on in parallel with our filtration project, and that's our unidirectional flushing program. So unidirectional flushing is used to kind of clear out distribution system pipes of sediments. And in the past, we've had a unidirectional flushing program, but it was sized that it would take about 70 years to make it through our system. So in the last year, we really ramped up this program. We have 4 crews now, and the goal is that they will make it through our entire system by the time the treatment plant comes online. So we really wanted that filtered water to enter into nice clean pipes, and that folks in their homes would be experiencing the filtered water and not have dirty water stirred up every time that there's a main break or a contractor uses a hydrant. So that's a program that we have going on in parallel with our filtration project. Next slide, please. So I'll just give a little bit of an overview of our pilot study. So our pilot plant is a mini treatment plant that is going to inform the large scale plant. It treats about 20 GPM, and it's about the treatment plant is going to be about 5,000 times larger than our pilot plant. The schedule that we're on, this diagram kind of shows the schedule of the whole filtration plant. But you can see that the pilot program really started up last July. We've been running for about a year. We just finished our kind of 1-year study of gathering regulatory data. We're going to be putting that together into a final report that's going to be submitted in November. Right now, we're starting to gear up to do a corrosion control bench testing study to really understand what the best corrosion control treatment will be for our filtered water. In the meantime, the pilot will still be used to kind of inform design And then once we have our pilot full treatment plant online, we can use the pilot plant to do process optimization. Next slide, please. So what are we piloting? So early on, the Bureau made a decision that we were going to be building a 145 mgd treatment plant using granular media, and that we would attempt to get rapid filtration filtration rates approved. So the pilot plant was really going to help us make some of those decisions, like, do we build a direct filtration plant, a conventional plant, or possibly a hybrid plant? Do we want to add ozone? And if we do, where would be the best place to add it? What kind of coagulant should we use? Do we need coagulant aids, filter aids? What should be the optimal filter loading rate? And of course, what kind of media should we be using in our filters? And we looked at GAC and anthracite. And then, the next phase is going to be what kind of corrosion control should we be looking at? Next slide, please. So there really are three main objectives of the treatment pilot study. So the first is the regulatory compliance piece. So that is for us to produce the data that we need to get regulatory approval for the full-scale plant that we want to design. The second piece is to inform, design. So there's lots of decisions to be made in design that we're hoping that the pilot plant can give really good information for us, that we can make the best decisions for the final design. And then the third is that it's a great opportunity to train our operators on the different processes that we're going to be putting into our full-scale plant. So at this point, I'm going to hand it over to Lynn.
Thanks, Yana. Can you guys hear me okay? Got a bunch of different screens, so just making sure.
Yes,
okay.
We can hear you well.
Okay, good. Okay, so the pilot needed to be placed at headworks so that it could be upstream of chlorination and receive raw water. There was not an existing facility on site that could house the pilot equipment. And so it was important to consider, both for the design, the long-term nature of this, that it's going to be, if you think of that schedule that Yona showed, 10 years at the headworks site, and then it's going to be transferred to the new water treatment plant location at Carpenter Lane. We also designed the pilot equipment to handle the proposed test regime for this first year, but also to be flexible for long-term testing over that 10-year and longer period. So basically, you can think of this as like a design build project. So BC put together the design, which included a new electrical source. We needed to bring in 480 volt three-phase power, which is coming in from the left of the photo. And then we worked with Sandy River crew. They constructed it, and they were pretty amazing. The pilot enclosures are the two boxes in blue that house the pilot equipment plus a lab bench. And then we have a shipping container for additional chemical and equipment storage that also includes an additional lab space. The blue large tank to the furthest left is a large baker tank used to settle out solids. And then, just given the remoteness of the site, in addition to the electrical supply, there's a generator, and that's housed under the blue roof to the farthest left. So going into the program management role in designing the pilot equipment, PWB had selected granular media filtration, but pre-treatment had not been decided, nor the media type or filter media, as Yona had mentioned. And the pilot's role is to inform these decisions. So through several discussions, we determined it was important to evaluate direct and conventional treatment, as well as pre and intermediate ozonation, and to look at alternative oxidants. So dual treatment trains were selected to directly compare treatment processes side by side for selection of the treatment processes for the full-scale facility. So pilot hydraulics were designed in such a way that we could basically swap any of those pre-treatment processes And so this slide is showing the two trains. And the example, the first train, or train 1, is showing pre-ozonation followed by conventional treatment. And then train 2 is showing conventional treatment with intermediate ozonation. Each train had 3 filters dedicated to it, followed by a common backwash supply. And then the filter backwash and the settled solids were combined that went through a solids handling system, the Baker tank, followed by GAC treatment when we were pre-chlorinating. And then the decant from that solids handling system was combined with the filtered water and discharged to the Bull Run River. I'm just gonna real quick kind of walk through the flexibility and what the system looks like. So this shows a photo of the ozone skid. There are 2 separate ozone contactors that are each dedicated to each treatment train. Like I said, both systems can operate in pre-ozone mode, or they can be in intermediate mode, or as this example shows, pre-ozone in one train. And then we could also dose alternative pre-oxidants such as chlorine, and then use the contact chambers for CT. And then we could bypass the oxidation systems completely. The next slide shows the sedimentation system. So there's 2 flock-sed skids that are shown in the photo on the left. And this is showing the one side where you can view actually the flocculation basins and the settled solids that are being produced. And then on the photo on the right, it shows kind of the backside of the skid where all the chem feed and monitoring is located. And then this example is just showing train 1 in direct mode and train 2 in conventional. They could both be in direct or both be in conventional, or either or. Additionally, there are 6 filters, and like I said, we had dedicated 3 filters per train, and they were designed to allow for deep bed media. So this slide again just provides an overview of the pilot, and each train is configured for multiple chemical feed locations and multiple chemical feeds. So once the pilot was designed and configured for the operational flexibility, and before the equipment even arrived on site, we did some factory testing, just like you would do full scale, to get familiar with the equipment, identify corrections, educate ourselves on the pop-up assembly, and also unloading and loading of the equipment. There is a lot to consider for coordination, communication, and pre-design of how to get the equipment into the watershed. The enclosures actually are oversized load, so we had to work with multiple states and DOTs to get approval to travel from Utah to Oregon. And then the timing was critical with basically the crane rental. Additionally, given the seismic nature of the site, placement of the trailers, we had cast in place concrete to tie down the enclosures. And additionally, we had to add seismic bracing within the enclosures themselves compared to what Intuitech typically includes. And so there was a lot of design coordination details that went into the permitting and approval. So even though this was a pilot, just like a full-scale facility, there were a lot of permit approvals and process to consider. And then just given the nature of the amount of hairpin turns in the watershed, I definitely felt a sigh of relief when the equipment was actually in place and on the ground, and the Sandy River crew was starting to connect things. Okay, so we knew we would get good water quality information, so we really gauged pilot success, making sure that the folks who are operating the pilot are safe, and that we are also being protective of aquatic life. So the goal was to really be safe by design instead of entirely relying on PPE. And so I'll just kind of walk through some of those considerations. You know, a pilot facility should have similar health and safety considerations that you have for a full-scale plant. We're dealing with all the same water treatment chemicals as a full-scale facility, even more so because we tested 4 coagulants, multiple polymers and oxidants. So at Headworks, there wasn't enough existing flow and pressure to serve a combination safety shower eye wash. So we actually designed a standalone unit that you can see in the photo on the left between the 2 enclosures. And placement of the shower was carefully considered to make sure we were within OSHA standards and accessible of those 3 enclosures where chemicals are handled. We also have bottle eye washes within several locations within the enclosures. Even though they're really small, chem feed metering pumps and chem tanks, they all have secondary containment. All of the chemicals that we are using in dosing for the pilot have containment, and then spill pads are also included within the enclosure. We have put together a detailed health and safety plan, a pilot work plan, an operational plan, and detailed SOPs to really make sure everyone understood, what we are trying to accomplish. The photo on the right actually shows working on filling filter media. So Intuitech's actual platform that they designed doesn't actually meet OSHA standards. So we worked on designing proper anchoring with the enclosures so that harnesses could be used when loading filter media. And we worked really closely with PWB's site safety officer. Given the remoteness of the watershed and the proximity to, medical care, being about an hour away, we developed a best practice of having 2 people on site for the pilot operation. And as you'll see, there's lots of moving parts with this pilot and a lot of water quality data that we are collecting that, at times this was just often needed. So another uniqueness of piloting up at Headworks for Portland is there's no existing sewer at the Headworks. So we worked with DEQ to get a mutual agreement order, or MAO, to allow for discharge from the pilot into the Bull Run River. This also included a public comment period. So this is pretty critical when Yona showed the schedule to just make sure that we were still meeting the agreement with OHA to deliver the pilot study report that had been agreed upon before we even kicked off this project. So I've done quite a few pilots, but this was my first to have its own discharge. And so through that MEO, we do daily sampling anytime we're taking water quality measurements and operating with chemicals. So basically we look at the total flow discharge. We need to keep the pH between 6 and 9 and have no detectable chlorine residual. In addition to the requirements of the MAO, the Bull Run River has ESA listed fish. So we also collaborated with PWB's Resource Protection Group to monitor for dissolved oxygen concentrations and to assess whether the discharge was having any impact on aquatic life. We also did a really detailed fish toxicity evaluation, looking at the treatment chemicals that we are utilizing and what concentrations should be expected following the treatment process. And that was a unique consideration for this. Some of the concentration levels that would be protective of public health, might not be protective for aquatic life when looking at that LD50 levels. So just an additional consideration as a part of this pilot. Some other important logistics to think through is training. We did a 3-day training that was conducted to educate staff. Each team member would sign off on SOPs before completing the task, keeping health and safety in mind. And The pilot team includes Headworks operators who would rotate in 4 to 6 week rotations. And so it was the main goal of this was to be a long-term educational tool for PWB and to learn about a conventional filtration facility. So we've learned a ton, and Mac will talk more about some of those findings. One area where a pilot differs from a full-scale facility is in chemical preparation. So instead of having large, bulk storage and day tanks, sometimes we're using 5-gallon chemical containers for filter aid, for example, and diluting them by hand or using drill mixers. And so there's just, important safety considerations with that. Throughout piloting, when operating, we varied the treatment processes and their order. We also varied, the flow and design conditions, and to assess their impact on water quality. And staff were also getting familiar with ozone as a treatment chemical. So the photo on the right shows John with an ozone sniffer. We also had dual ambient ozone monitors, because there's going to be ozone leaks. It's just the nature of the system, and so it's important to be prepared for that situation. We also had audible and visible alarms if an ambient ozone level was triggered. And then obviously these photos are pre-COVID. We also did a lot of monitoring. The pilot equipment is configured with several online analyzers. And we designed the pilot to be able to add additional monitors to assess the coagulation process. So one thing that's unique about this raw water source is that the turbidity is extremely low, and that's why they've been able to be unfiltered for so long. And so you're actually adding turbidity through the treatment process. So through coagulation, flocculation, and sedimentation, your turbidity is actually increasing. And it's really not, the settled water turbidity is really not the best gauge of the performance of that treatment process. And so we ended up using streaming current monitors and data sizers to really assess the effectiveness of that. There was also remote monitoring capabilities so that we could operate continuously, and Headworks staff could view operation from their desk. This allowed us to do like our spiking study and to make adjustments in real time. An important logistical item was just working with IT so that everyone who's remote, including the equipment vendor and Brown and Caldwell, could access the equipment remotely and be protective of cybersecurity. There were also several bench scale monitors, which is shown in the photo in the lower left. And then all the instruments were calibrated, verified, and trended. The pilot is producing water, but it's not actually being water that goes to customers. What the pilot is producing is information. And so, the importance of the accuracy of the monitoring equipment and the sampling is paramount to make sure you're producing reliable information. We did a ton of sampling through this process to monitor the effectiveness of the treatment processes and the changes that we were making. We were able to continuously monitor up to 80 parameters, measuring, field parameters daily and weekly sampling. The photo on the lower right is Anna doing simulated distribution system sampling. And then Tom in the larger photo is like a typical weekly sampling event. And then Max doing some aliquoting for sample jars for total metals. In addition to sampling and monitoring, data is collected every 5 minutes. So we had pretty extensive QA/QC, daily operational summaries, and weekly operational calls to discuss the data collection, and then a really thorough operational log so that we could determine, what filter runs were accurate, which ones should be removed because maybe we manually triggered a backwash, for example. We used R for our data reporting and assessment, just given the sheer magnitude of the data needed to be analyzed. And we had monthly piloting reports that we reviewed and discussed with the technical advisory committee and then the design team. And then we published an interim pilot study report, and we're working on the final pilot study report. So these are just the two figures that are example metrics that we used. Just like a full-scale plant, a pilot needs maintenance, and we developed, a maintenance schedule. Except for the photo of Umberto on the right with the raw water strainer, all of these photos represent something that Mac, who's our next speaker, broke through operation, which is, totally fine. That's how we're learning and gaining valuable information on how to operate this equipment. But again, maintenance is really important because data is only as good as the quality of the data you're collecting. So now I'm going to hand it back over to Yona, who's going to talk about some additional logistical considerations when dealing with the pandemic.
Yeah, so just really quickly, Lynn had already mentioned COVID. So when COVID hit in March, that kind of we had to scramble a little bit to kind of switch things up. The most important thing was that as the Bureau and the city was kind of really cutting back on projects and work that was deemed non-essential, was getting the pilot deemed to be an essential project, which it was because we're collecting the regulatory data so that we can meet all of our deadlines for the filtration project to remain on its compliance schedule. So one of the first things that happened is that the water treatment operators who had been rotating through the pilot were taken out of the pilot. We really basically put up kind of a wall between the pilot and then the folks that work at Headworks because they really are some of our most essential employees. So we just wanted to make sure that they were kept isolated from all the folks working in the pilot. We broke our team into two teams. We had our A team, which was Tom and Melanie, and then our B team, which is Mushtaba and Umberto. And Tom and Melanie worked on Mondays and Tuesdays, and Mushtaba and Umberto worked on Thursdays and Fridays. And we really kept them separately. Everybody drove up in separate vehicles, and then and maintained social distancing while working in the pilot. And really importantly, wearing masks all the time. You can tell in any photo if it's pre or post-COVID by if folks are wearing those masks. And then another thing is our lab had kind of limited capacity. And so we really had to rethink which of our samples were the most criticals to send to our lab. So next slide, please. So really quick, I think we're almost out of time. Some takeaways from this project was, it was really the good planning from Lynn and her team and folks at the Bureau that allowed the pilot study to be successful, that we can collect the information in the kind of tight deadline that we were in, which was to complete all this work within 1 year. It was really important to think through all the details of the pilot, kind of like you would for a full-scale water treatment plant. Lynn mentioned that we had these 2 treatment trains, which was really beneficial in being able to compare different processes side by side. I think most importantly, it was the strong collaborative team, which was what made this project a success and allowed us to collect valuable information that we can use to inform the decision-making for the full-scale plant. We learned a lot of lessons. It was a great training tool for staff, and hopefully will give us the regulatory approvals to have high rate filtration. So I'd just like to end with just an acknowledgement of all the folks that helped make this project a success. We had folks from the water quality group, from our treatment and process engineering group, our engineering team that is heading up the filtration project. Our lab processed hundreds, if not thousands of samples. Lynn had already mentioned our resource protection group that helped with our discharge issues, as well as Sandy River Station, who helped us install basically everything. Of course, our partnership with Brown and Caldwell, with them helping design the study plan, help us at the pilot, looking at the data and now putting together the report for us, working with us on that. The folks at Intuitech, who of course built the pilot, and we've recently started working with our design team to get their input. And Lynn had mentioned also we put together a technical advisory committee with a couple national experts who were able to give us feedback on our plan and on our data as we were analyzing it. So definitely wouldn't have been able to get through this project without the help of all of these folks, some of whom are in these photos. I think that's it, and I believe we're going to go right into Mac's presentation and then save the Q&A to the end of both presentations.
Yes, that's correct. I think that's a good idea. So Mac, you can go ahead and take over the screen share if that's the plan, and just try and keep it so that we can still close out by noon if possible.
Spectacular. Thank you so much, Josh. Let me make sure I've got this all set up right. So I'm sharing that screen. There we go. All right, can you guys hear me and can you see the slides?
I can hear you. I can see you. I still see the acknowledgements slide. I don't know if we're still waiting for that to update or what. I'm still seeing Lynn's screen. Oh, there we go. It's swapping now.
There we go. All right, there you go. Yeah, now do you see the full scale?
Yes, it looks good. Thank you.
Spectacular. Thank you so much. So my name is Mac, and I work for the Portland Water Bureau. I work with Yona in the Regulatory Compliance Group, and had the honor to be the operations lead on this great project. So my objective here today, now that Lynn and Yona have got us so well set up, is what can we actually learn with it now that all this stuff's in place? What lessons can we actually learn? So I'm going to go through what some of the exciting findings that we've been able to produce over the last year as we've been working towards gaining regulatory approval, as we've been informing process selection. Going to touch on how we approached the questions, some of the results that we found around turbidity, ozonation, DVPs, and filter media, and then quickly on our path forward from here. So let's talk about the operational approach. We needed to get this thing on and running and needed to have a plan for gathering interesting information that was helpful, as they've well covered. The pilot has dual treatment trains, which really worked well to allow us to compare two different variables side by side at the same time. Each of those trains would feed 3 filters, and we kind of rebuilt the filters at one point in the middle of the project. So the filters shown on the left, the 6 on the left, are when we started up, those were kind of the filter designs that were on each train. And then about halfway through, we shifted to the set of 6 on the right. We rebuilt the filters. What's important here is that we were able to test, again, side by side, which filter media, GAC versus anthracite, different loading rates, 8 to 10 to 12 GPM per square foot, different depths and sizes of media. So what was really interesting here was the ability to be able to make some of those comparisons to inform our process selection on what kind of filters we eventually want to build. The kind of water that we're treating, similar to a lot of people that have talked today, amazing raw water quality. We have very cold, very clean water that has low alkalinity, has low turbidity, pretty low organics also. Interestingly, the total particle counts, there's very few particles. Very clean water means that there's very few particles coming into the pilot, which interestingly makes it mathematically difficult to show proper log removal. And we'll talk about how we kind of got around that. We had to set, at the onset of the project, we had to set a whole bunch of goals. And here's a quick summary of what some of our specific water treatment goals were. We had to establish thresholds to know whether something was working well or not. The kind of 4 big ones highlighted here. First is turbidity, and our goals there are set around the Partnership for Safe Water and the area-wide optimization program. I think a lot of folks are probably familiar with. Somewhat interestingly, though, since one of the big drivers for filtration for us is control of cryptosporidium, we certainly weren't going to bring crypto into the watershed to put into the pilot. So instead, we use particle counts as a surrogate for crypto. So any particle that comes through that's in the same size range as crypto, and then also Giardia, we watch those particle counts of those same sizes to know if we're providing adequate treatment for removal of those pathogens. And then also another really important driver for providing filtration treatment over other ways of treating for crypto was the ability to reduce disinfection byproducts. So we have the goal to make significant reductions to our disinfection byproducts. And then this was the baseline chemistry, a summary of the baseline chemistry that went into running every other comparison and experiment that we ended up doing. This in and of itself could have been an entire lecture. We did a very detailed coagulant investigation to know which sort of primary coagulant we should be using and at what kind of doses. The short version is that we found a lot of options that worked well. We ended up having to just pick one that we could use as a baseline to make other comparisons with. We went with polyaluminum chloride, PaCl, primarily because it doesn't consume alkalinity the same way, doesn't require the same sort of pH control as other coagulants. We made it operationally easier to handle. We use a little bit of coagulant aid and a touch of non-ionic filter aid when it gets to the filters, both help filterability and controlling filter effluent quality. And then ozone dosing, similar to the approach that Kim and Carrie described earlier on the webinar, we use for particle conditioning more than for disinfection. So really low doses of ozone, targeting low residuals after the contactors. So with all that, what can we actually learn? What were some of the interesting results that we found? I've got this organized into 4 different questions. 4 of the questions we were trying to answer at project onset. What are some of the benefits for turbidity control? How much value does ozone bring? What are the benefits for disinfection byproducts? And which filter media has the most value? So let's start with, what are the benefits for turbidity control? To give you some context, why it matters to control sediment in our distribution system. Currently today, as an unfiltered system, the water we serve has somewhere in the neighborhood of about 0.5 part per million worth of total suspended solids in it. That's not very much, but when it's extrapolated out across the 31 billion gallons per year that we serve over the course of an average year, that says that we're putting about 65 tons worth of dry material, dry sediment out into our distribution system every year. And that's been every year for 100 years. So part of that speaks to the importance of the unidirectional flushing program that Yona mentions and the need to clean that all out, but also the opportunity that we have moving into the future as a filtered system to avoid putting all that dirt out there. So one of my favorite spots to stand in the pilot is right here at the base of the filters, where you can see the filter effluent turbidities that are coming off those filters and really low numbers, very low turbidity. The quick takeaway message being conventional treatment and can produce even lower turbidity for the water that we're serving today compared to the water we're serving today. So let's start to put some graphs and numbers to all of that. This is an example of a filter run, and we've looked at literally thousands of these over the last year. I'll call your attention first to all the green dots, which are the turbidity over shown on the right axis. The point there is that the turbidity coming out of this filter was very low, in this case around 0.05 for a very extended duration, for over 25 hours. It was able to produce that water. As you get towards the end of a filter run, that turbidity starts to break through. The filter's capacity to hold particles reaches its capacity, so the turbidity starts to break through. If you're doing it just right, your head loss also reaches its terminal levels, and that's represented in that red line. You see that red line increases linearly as you develop head loss in your filter, more and more pressure required to push the water through the filter until it reaches a terminal. We're using a threshold of 12 feet worth of head loss before we backwash. Also important to understand here is the relationship with the unit filter run volume. The filtration rate shown in the yellow dots combined with the length of the run to let you know how much volume of water you produced. By normalizing it to UFRV, unit filter run volume, that takes into account both run length and run rate. It tells you what the total volume of water you produced were during that run. And as a UFRV of around 16,000 in this case was really good. The takeaway message from all of this is that the filtration does in fact provide excellent solids control, and we are able to produce very low turbidity water. As a fun thing, just recently we completed a spiking study where we artificially increased the turbidity of the water coming into the pilot. We used soil from the watershed in order to simulate what a turbidity event, a high turbidity event might be. And that jar on the right is about 100 NTU that we were able to show it. And then those other grab samples through the treatment process really visually capture the real value of having some treatment, having this conventional treatment in place. And you see it got down to drinking water acceptable levels by the time it got out of the filters there. Also able to demonstrate by increasing the level of influent particles, we could actually demonstrate a higher level of log removal than we were otherwise able to do, and able to finally show greater than 3 log removal worth of particles. Let's go that way instead. So moving on to question number 2, how much value does ozone provide? So now instead of a single filter run, these graphs are showing multiple filter runs over time, all from the same filter. The top 2 graphs are showing turbidity, similar to how we were looking at before. And we were able to show or run the filter for a few weeks, or it's a 1 week on this graph with no pre-oxidation at all. And what you can see on that graph on the top left is the turbidity kept spiking up. It was very variable. The runs were a little shorter and the turbidity kept breaking through very quickly. With no other changes to chemistry or process, we were except for turning on ozone, that low preconditioning dose we talked about. There's that same filter operating under the same conditions there on the top right. And what you immediately see is that the turbidity came right in under control. And then that ozone really helped control that, improve the filter effluent turbidity. The set of graphs on the bottom are now particle counts. So instead of the gross metric of turbidity, we're looking at sort of the finer tuned in metric of particle counts that are broken up by different size ranges. The 3 to 5 and 5 to 15 size ranges chosen to indicate, to represent cryptosporidium and giardia, or the gray dots that are the total particle counts. And the takeaway message there is the same, is that without ozone on the left, really had, it was much more challenging to keep particles in the filter effluent very low, whereas with that preconditioning ozone dose, what was very successful in keeping those particle counts low. So the takeaway message there is that that ozone improves filter effluent quality quite a good deal. But there's also a second benefit that we've been able to find to ozone, and that's in not only effluent quality, but also in productivity. What this graph is showing is essentially a summary of many different runs and how long they went. Going back to that metric of UFRV, that's what's being graphed here. So a high UFRV is a good thing. That means filter is being very productive. And for the 6 filters that were being studied at this time, you see that the 3 boxes on the left, draw your attention particularly to that thick line in the middle, which represents the median of many different filter runs. But that thick line in the middle of the box, for the 3 filters on the left, you'll see are all higher, all have higher productivity UFRVs than the 3 filters over on the right, which had no pre-oxidant. Running those side by side, it became starkly very, very clear very quickly that that having that ozone improved filter productivity, very drastically. So we're able to show that pre-ozone for our water really improved both effluent quality as well as productivity. I think other utilities have other pre-oxidants. There are other options out there that hopefully we'll get a chance to explore more. Also, and other utilities might use other oxidants and see if they get similar benefits. All right, question number 3. We've said that one of the project goals is to improve disinfection byproducts. What are the benefits towards disinfection byproducts? This was one of my favorite graphs. I was absolutely thrilled when we did this. And a shout out to start it with to my colleague Anna Vosa, who ran the fairly complicated procedure that it takes to simulate a distribution system to know what disinfection byproducts might be coming out of a treatment plant. Let me walk you through what this graph shows you though. The set of, we're looking at haloacetic acids in this graph, and the set of bars on the far left at lusted outlet, that's our current entry point to our distribution system today. And so that water sample is representative of our current water. And so that water was sampled, put in a jar, allowed to sit for 14 days and see what the HAs were. This was also during our fall season, so those are kind of the highest levels of DVPs you might see in our distribution system, meant to be sort of the extremes. So what you see is that those were very high. Next to that, we now have the raw water, and so what we did there, instead of our current disinfection, full-scale disinfection, has a pretty high CT, and so when we centralize our treatment, we'll also probably be able to optimize that CT a little bit more. So that second sample that says raw water illustrates if we had our raw water and we ran a disinfection similar to what we might expect might happen at the full-scale facility. So we're reducing that CT to just what we need instead of over disinfecting. There's some benefit going between those first two samples in reducing DVPs. So that's already a good thing, just by centralizing treatment. But the real message of this slide is, okay, so what does the treatment itself actually provide? And so we can see that by comparing that raw water sample to the 6 filter effluents. And the very clear message is disinfection byproducts are drastically improved through the conventional treatment process. In this case, we had 3 of the filters that had pre-ozone turned on, 3 of the filters that had no pre-oxidation. And in both cases, we had very drastic reduction in haloacetic acids, which is excellent. And we really hope that leads to public health benefit for the million people that drink our water every day. Similar graph here for trihalomethanes from the same sampling event. Again, you see improvements just by centralizing treatments, but then drastic reductions by going through the treatment process, which is excellent. All right, last question. Which filter has the most value, or which filter media specifically? We were tasked with exploring granular media filtration, but there's a lot of questions on what that means. Which media, how deep, how fast, how big is each granule? A whole bunch of questions like that. So I'll focus today on just the question about which media. The 2 that we compared side by side through the first half of the project was anthracite versus granular activated carbon. Those are the 2 big options out there. And here I've got representative runs from 2 of those filters, from an anthracite filter, from a GAC filter that otherwise had the same upstream treatment, but we're able to compare how well they each did. So looking at the effluent, the green dots, the effluent turbidity, they both were able to meet excellent water quality for an extended duration. Either one would have worked very well to produce clean water. But what you do see is that the anthracite filter lasted a bit longer. Given the same filtration rate, it went a little longer, which meant that it had a higher UFRV, higher productivity. Part of the reason for that is that we struggled to control clean bed head loss with the GAC filter. You can see where the red line on the graph on the right intercepts on the y-axis. It's clear up there at 6 feet, whereas the anthracite filter over on the left is intercepting that axis over at 5 feet. So that's a foot worth of head loss that it wasn't able to accumulate during its filter run. So we might have been able to learn how to mitigate or manage or operate around that better given more time. But for the time being, the takeaway was that anthracite filters generally had a lot higher UFRVs than the corresponding GAC filters. There was a bit of a trade-off with all that, though, with organics control. So on this graph, what we're looking at is over a long period of time, a few months, we wanted to compare the level of organics coming into the pilot in the blue dots coming out of the settling basin is sort of those pink purple dots. But really the message is between the anthracite filters in the reddish salmon colored dots and the GAC filters, the corresponding GAC filters in the green dots. What becomes visible is that the GAC filters consistently had a lower level of TOC in the filter effluent than the anthracite. Again, both performed excellently. Either one will work very well. But the takeaway message is that GAC did do better, as expected, as it should. That's what GAC is for. Did do better with organics control. So to summarize all of that, we did a detailed comparison with anthracite and GAC. The takeaway messages here is that both did well in terms of filter effluent quality and UFRVs. Anthracite had higher UFRVs. GAC generally had better organics control, including disinfection byproduct control. But they were similar enough that we could kind of make the decision based on cost. And GAC is a higher cost product than anthracite is. So based on that, we were able to select that we wanted to focus on anthracite filters moving forward. And so we've done that. That's why we rebuilt the filters to have 6 anthracite filters, which we continue to investigate until today. All right, so that's it. Let me wrap up with a few last conclusions, parting thoughts. Answering some of those questions. Some of the answers we've been able to discover with the treatment pilot is learning that there really is a variety of treatment approaches that are able to help us meet our water quality goals. We have been able to demonstrate that we can control particles that are the same size as cryptosporidium. We've been able to demonstrate that we can serve bull run water even when the influent turbidity exceeds levels that we can serve it at currently today as an unfiltered system. And we've really learned the importance of coagulation chemistry, and there's lots of stories to go into with that. What's the value of ozone? We've demonstrated that ozone can both improve filter effluent quality as well as filter productivity. Is there value to disinfection byproducts? There is. We really expect significantly improved disinfection byproducts as a result of enacting granular media filtration. And for filter media, we've chosen to focus on anthracite filters to provide the most value. So we got years worth of piloting to come. In the short term, we're talking about, we'll continue to inform the design of the full-scale facility. Some of the questions coming up soon are, what are we going to do about corrosion control and disinfection? We want to learn more about the ranges of chemical injection that we might need at different spots in the filters in the process train, as well as solids generation. And we'll continue to provide operational optimization and continue to learn lessons about running a filtration facility and training staff. So super appreciate everyone's time. Hopefully you've caught a little glimpse of the excitement on that project, where we're excited to be able to find ways to learn to make the best water in the world even better.
Thanks, Mac. Really appreciate you and Yona and Lynn's time in presenting this material. Is there any questions from the crowd in our last couple minutes before we close out? Looks like Ray Leopold was asking if we'd made any decision about conventional versus direct filtration so far.
Mac, do you want to lead that? Or I guess I could just say, I was talking about the capabilities of us being able to do that test, but we have chosen conventional treatment. We've seen a lot of value from having that in the pilot in terms of our filtration performance, as well as resiliency for future events, such as storms or, landslides or potential forest fires. Anything, Mac or Yona, you want to add related to that?
I'll just add real quick, Lynn, that the decision that was made was not necessarily made on data coming out of the pilot, but more a decision that the Bureau made on how we wanted to handle risk in future events.
Thanks, everyone. There's a question from Casey Shankland asking about solids handling. I'm guessing that question is kind of like how are solids handled during the pilot, and if you have a plan for the full-size plant so far.
Yeah, so I guess I'll tackle the pilot. we used a large settling tank, and then had the option of going through through GAC contactors for dechlorination, for passive dechlorination, where chem feed couldn't actually be turned off and have an issue with chlorine residual. Full scale, just given the site constraints, we're looking at mechanical dewatering for solids handling, and we've been collecting solids and analyzing that to send for further assessment through this pilot.
Makes sense. Thank you. And I had one final question I had was on biological filtration, and if you'd gotten any results one way or another on how effective that might be.
Yeah, we really have. So we do monitor biological activity in the filters pretty closely, and we do a lot of stuff with ATP monitoring and the aqueous and attached onto the filter media, and they're not doing anything to prevent biological filtration. So I think we are getting some degree of stabilization, be that biological stabilization, reduced chlorine demand, better organics removal. Those are all in there. We do have pretty cold water with low organics, and so it's certainly not the most biological active filters in the world. But we want to be active in managing it too. Perhaps part of the reason why we struggled with clean bed head loss on the GAC filters is might be connected to that biological activity, but we haven't yet. We will in years to come have the opportunity to have enough time to dive into really optimizing, to getting to that level of optimization. Whereas right now we just have to focus on which filters we're even building.
Yeah, makes sense. All right, thanks everyone. We're getting past the time, so I just wanted to thank all our presenters. There's a lot of good feedback in the comments about everyone appreciating all the presentations. Those that were looking for PDH and CEU credits should receive a certificate within 30 days. We'll try and get them out a little sooner than that, and we'll reach out to you if you need any more information, obviously. And then the last thing I wanted to part with was we have one more workshop coming up on August 20th. We'll be sending out the information on that soon, so stay tuned. And please sign up and join us for our last one for the Water Treatment Committee. Thanks again, everyone, for joining us, and take care.
Thank you so much, Josh.
Thanks, Josh.